everyone. Am I audible? Right. Is my screen visible to all? Yes, yes. Yeah, yes, 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 yes. Right. Thank you. Actually, it's raining heavily at my place, so that's why there was a supply issue from last, I think, 1.5 hours. Okay. So, anyways, so from today onwards, we'll be conducting the lectures on sketchbook, right? Yeah. Okay. So I think most of you might be happy with the sketchbook. Most of the students were demanding for the sketchbook, right? Okay. Yeah. So in the yesterday's session, we discussed about, yes, yes, yes. Okay. In the yesterday's session, we discussed about thyristor, that is the SCR. Already we have discussed about the power diode. We are having, as long as your syllabus is considered, we are having a detailed analysis of a SCR, and that analysis was completed yesterday. In today's session, we are going to discuss the remaining switching devices, just like a power BJT, power MOSFET, IGBT, GTO, and a TRIAC. Okay, these 5 devices we are going to discuss. And after the completion of these devices, we'll be starting the second chapter, that is the AC to DC converter, right? So let us put the heading power BJT, power BJT. Right? So BJT stands for bipolar junction transistor. Okay. But here in the name, there is a bipolar. So it doesn't mean that this is a bipolar device, right? As long as power BJT is considered, it is a unipolar device only. Why it is a unipolar, we'll discuss, right? So next. So the basic construction of power BJT. Yes. So suppose we are having a BJT N plus layer, thick N minus layer, next P plus layer, and N plus layer, right? So this is the basic construction of a BJT, right? So terminals are collector, emitter, and a base. So the difference between your signal level BJT and a power BJT is, here N minus, we are having a thickest N minus layer. What is the purpose of adding the N minus layer? Yes, because as long as our power devices are considered in power electronics, we are using these devices as a switch only now, right? So here these devices should behave as a switch, means either on state or off state, that's it, right? Either on state or off state. Okay, so here if the switch is in a off state, so in order to block the high voltage, because in a power electronics we are dealing with the high voltage, high current, right? So if the switch is in an off state, in order to block that high voltage, yes, generally we add the N minus layer here, and the width of the N minus layer decides how much voltage our device can block. Are you getting the point, right? So let me write this. Yes, the width of N minus layer decides the voltage blocking capacity. The voltage blocking capacity of device, right? So more the width of N minus layer, more will be the voltage blocking capacity of the device, right? Now, so let us first discuss, yes, definitely the symbol of the device, we know the symbol is same as that of your signal level device symbol. It is a 3-terminal device. 3 terminals are, yes, base, collector and emitter. Okay, so this is a collector, here it is a emitter, and here it is a base wire, right? So let us discuss why this device is not blocking the reverse voltages, right? Very important point, because most of the students are having the confusion. In the signal level, you might have studied that during the off state, the device blocks the reverse voltage also. But here in a power electronics, I am saying that this device is not able, this device is not blocking the reverse voltage. Okay, so why it will not block the reverse voltage? Let us discuss. So first of all, suppose we have maintained, let me see, yes. So suppose we are having a load here and a DC voltage connected here, right? Suppose this is plus minus, this is a VCE, okay? And this is load resistor RL. Consider this voltage is a VS. Let us consider this voltage is a VS. So now you can check, this is a higher potential, here it is a lower potential, okay? So it is like a higher, initially device will be in the off state only, right? So you can check here, this higher potential will appear at the collector, so it is a plus here. This lower potential will appear at the emitter terminal, okay? So can we say that from collector to emitter, the potential go on decreasing, right? Collector to emitter, potential decreases, right? So here in the BJT, how many junctions we are having? You can check here, whether this n plus n minus, whether it will form a junction, whether the n plus n minus, it will form a junction. Both sides were having a n type layer, na? So definitely it will not form a junction, right? So please keep it in mind. Junction will be there, will be present only when one p type and one n type layer will be there. Okay, so here we are having the both these sides, that is a n plus and a n minus, both are the n type layers, so that's why this is not a junction. Next we can check n minus p plus, this is a junction, let me write it as a J1. P plus n plus, this is a junction J2. Okay, so now we have maintained the forward voltage. Forward voltage means collector is at higher potential, emitter is at lower potential. Okay, from collector to emitter the potential is decreasing. Okay, so potential is decreasing means, can we say that here n minus potential will be higher than that of your p plus layer? So n minus is at higher potential than that of the p plus. So can we say that junction J1 will be in the reverse bias mode? Okay, so junction J1 is in a reverse bias mode. Junction J2, p type is at higher potential, n type will be at a lesser potential. So junction J2 will be in a forward bias mode. Okay, so when VCE is positive, can we say that junction J1 forward bias, junction J2 reverse bias? So let me write it. Yes, when VCE is a positive, means device is in a forward bias mode. Okay, so therefore device, that is BJT, okay, is in forward bias mode. Forward bias mode. Okay, so when VC is positive, we know it is a junction J1 reverse bias and junction J2 forward bias. Now you can check at the junction J1. At the junction J1, we are having a junction J1 is nothing but at one side we are having a n minus layer. At second side we are having a p plus layer. The n minus layer is a lightly doped and its width is a high. Its width is a comparative to the other layers. Okay, the width of the n minus layer is intentionally we have kept high. Okay, so here you can check, even though the supply voltage is high, here as this junction J1 is in a reverse bias mode, whatever the depletion layer will be there across junction J1, that depletion layer width go on increasing, and whether that depletion layer is having a scope to grow, yes, that depletion layer is definitely is having a scope to grow. Why I'm saying that depletion layer has a scope to grow? Because you can check here the width of the n minus layer is very high now. So here you can check junction J1, here it is a n minus, here it is a p plus. Okay, so as we go on increasing this voltage, as we go on increasing this forward voltage, definitely the width of the reverse bias junction J1 depletion layer width increases. So depletion layer width will increase for to how much maximum value it will increase. It depends on the width of this n minus layer. So here can we say that as the n minus layer is a part of that junction J1 and junction J1 is in a reverse bias mode. So that's why our device can successfully block the forward voltage, right? Device can successfully block the forward voltage. Are you getting the point, right? Because junction J1 reverse bias and junction J1 at one side we're having a n minus layer. N minus layer is a thick layer now we are having, right? So depletion layer is having a path available. Depletion layer is having a scope available, okay, to grow, right? So that's why here you can check due to this n minus layer, our junction J1 depletion layer across junction J1 can increase. So depletion layer junction J1 width depletion layer can increase. The meaning is we can increase the voltage to a maximum possible value. Okay, means our device can block the high voltage, right? So let me write. So therefore device can block high forward voltage, right? High forward voltage our device can block. Okay, now suppose as we know the BJT is a current control device. Okay, so suppose if I circulate the base current, okay, definitely here between base and emitter will be having the controlling circuit, right? We'll be having a controlling circuit. So it will be like this. Here it is, we are having the controlling resistor. Let us write it as a RB, and here it is a voltage source, right? So suppose this is a ES. Let me write it as a ES. Okay. So as I go on increasing this VBE, what is happening? Yes, indirectly you can check across junction J1 at this side we're having a layer of negative charges, na? At this side we're having a layer of positive charges. We already discussed. And when we inject these positive charges, when we inject the positive charges from the positive plate of the ES, these positive charges will be getting added into the P plus layer, and these positive charges will be recombining with whatever the negative charges those are present here. Yes or no, right? So the width of the depletion layer will decrease and our device can turn on. Okay, so now when device is in a reverse bias mode, then what will happen? Let us discuss. Okay, this is important actually. When device is in a reverse bias mode, then what will happen? Okay, so now suppose, yes, device is in a reverse bias mode. So let me redraw this. BJT is in reverse bias. Right. So we know BJT is same structure here we're having. Yes, it is a N plus N minus, right? P plus, and here it is a N plus. Here it is a collector. This is a emitter, and here it is a base, right? Now suppose device is in a, yes, device is in a reverse bias mode. Okay. So suppose this is minus here, plus here, this is a VS, and let us consider it as a RL. Okay. So now what will happen? Initially device is in an off state. So this minus will appear here, this plus will appear here. So can we say that from emitter to collector potential go on decreasing? Emitter to collector potential decreases. Okay. So we're having the junctions like this is like junction J1. This is your junction J2. So now can you tell me what about this N plus P plus junction, whether it will be forward bias or reverse bias? This junction will be in reverse bias, na? Junction J2 reverse bias. What about junction J1? P plus N minus. The junction J1 is forward bias. Now you can check here, we are having a junction J2. Across the junction J2 at one side we're having a P plus layer, and second side we're having a N plus layer. What about the widths of those layers? Those layers are heavily doped, and the widths of those layers are very less na, compared to the N minus. The widths of P plus and N plus are very less. So can we say that as the widths of these two layers are very less, and also these two layers are heavily doped, that's why this junction or the depletion layer which is present across junction J2, that depletion layer cannot block high voltage. Are you getting the point? If you compare the first case and this second case, in the first case, it was like a junction J1 was a reverse bias mode, and at junction J1 at one side, we had a N minus layer. So that's why the depletion layer had a scope to grow. But whereas you can check here in this case, junction J1 is already forward bias mode. So width of the depletion layer across junction J1, definitely it will decrease only. But junction J2 is in a reverse bias mode. And at junction J2, we don't have the N minus layer now. We're having a layer of N plus and the P plus layer. Okay. So that's why if we go on increasing this voltage, okay, our device will get damaged. Our device will get damaged. Are you getting the point? Right? Means whether our junction or whether the depletion layer will block the high voltage or not, it depends on that if that junction is in a reverse bias mode, and across that junction, if the lightly doped N minus layer is present, then and only then our device can block that voltage, high voltage I am saying. You can recall power diode. In a power diode, we are having a N minus layer sandwiched between P plus and N plus. Okay. So when device is in a reverse bias mode, what happened? That N minus layer was a part of that single junction only in power diode. You can recall SCR, silicon controlled rectifier. In a SCR, we are having three junctions. When SCR is in a forward bias mode, it is like a junction J1, junction J2, junction J3. J1, J3 forward bias, junction J2 reverse bias. But junction J2, the junction J2 which was in a reverse bias mode, for that junction J2, at one side we had a layer of N minus layer. We had a N minus layer. So that's why our device was blocking a high voltage. Similarly, you can check in the case of SCR, when SCR is in a reverse bias mode, it is like junction J1, J3. Okay, these two will be in a forward bias mode. Sorry, reverse bias mode. Junction J1, J3 reverse bias mode. Junction J2 forward bias mode. But whether N minus layer in a SCR, N minus layer is a part of junction J1. Yes, you can recall, right? N minus layer was a part of junction J1. So that's why in the reverse bias mode also, our SCR was able to block, right, that high voltage. But in this case, what will happen in the BJT? Okay, as this junction J2 across junction J2 we are having a heavily doped P type and N type layers. Okay, and the widths of these two layers are very less. Okay, so therefore this junction J2 will not block high voltage. Okay, will not block high voltage. So let me write here, as junction J2 is in reverse bias mode, is in reverse bias mode, and across junction J2, yes, heavily doped P type and N type, P type and N types layers, N type layers are present. Also, widths of these two layers, yes, is very less compared to N minus, right? Compared to N minus. So therefore, junction J2, yes, will not block high voltage. Junction J2, yes, high voltage. Is this clear? So that's why our BJT will not, we can say that with a negative voltage, our BJT can't even withstand. Okay, so please keep it in mind. As long as the power BJT is considered, here definitely the power should be there. Okay, as long as the power BJT is considered, okay, we can maintain only forward voltage across the BJT. If we apply the reverse voltage, our BJT will get damaged. Our BJT will get damaged. Okay, so that's why in the static operating points, okay, on VI plane, we discussed for a power BJT. Yes, it was like power BJT blocks only forward voltage and it allows only forward current, na, right? So it will not allow the reverse current even. Why? Because if the reverse voltage, if with a high reverse voltage, if our device is not able to withstand, then definitely the current also will not flow, na, right? For reverse current, definitely we need to maintain the reverse voltage, na, yes or no, right? So that's why here our device will only block the forward voltage and our device can allow the current only in a forward direction. Okay, so this is the thing regarding the power BJT. Next, now suppose if I apply the sinusoidal voltage across the power BJT, what will happen? If I maintain the sinusoidal voltage across the power BJT, what will happen? In a sinusoidal voltage also, we're having a positive cycle, we're having a negative cycle. Yes or no, right? In a positive cycle, it is like a, yes, in a positive cycle, it is like a VCE is positive. So for VCE positive, definitely our device will block that voltage. Yes or no? When device is in off state, our device will successfully block that voltage. But suppose during the negative cycle, during negative cycle means it is like equivalent circuit will be like this, na? Means VC is negative. So our device, yes, will not withstand with that negative half cycle, na? So that's why across power BJT, we cannot connect the sinusoidal supply also, right? So power BJT, for power BJT, we can connect only the positive voltage, that's it, okay? We cannot apply the reverse voltage, we cannot even apply the sinusoidal supply. So that's why if you check in the converters where the input is sinusoidal, in those converters, we are not using the power BJT. You can check the rectifier. In the rectifier circuitry, whether we are using the BJT, no, we are preferring the thyristor, we are preferring the SCR. Okay, because for this rectifier, the input is sinusoidal. Okay, and for sinusoidal input, during the negative half cycle of the sinusoidal supply, our BJT will not work, our BJT will get destroyed. Okay, due to the high voltage, right? Second thing, you can check AC voltage controller. AC voltage controller is a circuitry which converts fixed AC to variable AC. So input is AC, na? So in that case also, we are not allowed to use the power BJT, or we can't use the power BJT there also. But you can check DC to DC converter. You can check the inverter circuitries where input is DC. Okay, in that case, we can use the power BJT. Is this clear? Right? So let me write. Yes. If reverse voltage applied across power BJT, right? So power BJT will destroy. Okay, then device will get damaged. Okay, so therefore generally the negative voltage is avoided. Okay, so therefore generally negative voltage is avoided. Okay, but you can apply the small voltage, but as long as the power electronics is considered, because main purpose of the power electronics is to control and convert the large amount of electrical power, na? Means we are dealing with a high voltage only, right? So generally negative voltage is avoided, and also sinusoidal voltage is also avoided. Okay, next, sinusoidal voltage is also not allowed. Okay, not allowed. So this is about the BJT. Now let us discuss. This is the discussion regarding why the BJT is not blocking the reverse voltage, right? Let us discuss the power BJT output characteristics. Power BJT output characteristics. Power BJT output characteristics. So in this section, we are going to discuss why the continuous base current is required for the power BJT, And as long as the power BJT is used in the power electronics, because definitely we are using it as a switch now. So in which modes, whether it is a cutoff, whether it is a saturation, whether it is a active region, okay, so in which region we are supposed to maintain the device, okay, that we are going to discuss. So power BJT output characteristics. So for that, let us consider the circuit. So this is your collector, emitter, and here it is a base, right? So this is a RB. Let me write it as a B ES. We can consider it as a ES, right? This is like a load resistor, your RL, or you can consider this as a RC also, doesn't matter. This is a VCC. Suppose this voltage, yes, is a VCE, and this current is a IC. Okay, so characteristic we are having is like this. Yes. So yes, it is a plot between your output current and a output voltage, right? Output current and a output voltage. So it is a VCE versus IC. So characteristic is like this. Right. So right. So next. So this is the characteristic for different values of IB. VCE, that is the output voltage. Okay, that is the voltage across the device. VCE versus IC. Okay, VCE versus IC for the different values of IB. So let me consider this first one is for IB is equal to 0 ampere. Suppose this is for IB1, this is for IB2, IB3, and consider it is a IB4. IB4. Okay, because BJT is a current controlled device, right? BJT is a current controlled device, right? Next, now we are having here, yes, if IB is equal to 0, so whatever the region here, right? So this is the cutoff region. This is a cut off region. Next, yes, this region we are having, it is an active region. Let me indicate here. Yes, from here to here, this is a active region. Active region. Okay, and this is the saturation region. Saturation region. Okay, saturation region. Next, now, or it is also known as a hard saturation. And the second one we're having, it is like this. This is known as a quasi saturation. In your signal BJT, that quasi saturation region is not available. Okay, this full we indicate in a signal level devices as a saturation region only, right? Means it is like this type of. Okay, so now let us discuss this regarding about this circuit. Suppose if we apply KVL to this loop, if we apply the KVL to this loop, what will happen? Okay, so suppose KVL means plus VCC minus VCE minus IC into RL is equal to 0. Okay, so KVL to the output loop, output side, KVL to output side. So it will be like, we'll be getting it as a plus VCC, right, minus IC into RL minus VCE is equal to 0. Now from this equation, suppose if we keep IC is equal to 0, if we keep IC is equal to 0 ampere, then can we say that VCE is equal to VCC? VCE is equal to VCC. What this point indicates, at IC is 0 ampere, means current flowing through the device is 0. So can we say that it is like a device is in an off state? And what is this VCE? VCE is nothing but voltage across collector and emitter terminal of the device. Means can we say that it is nothing but the voltage blocked by the device? Are you getting the point? Okay. IC is 0 means device is in an off state, because you can check in a device on state, device off state. Device on state means it is like a voltage across device will be ideally speaking 0. Means VCE will be 0 if a device is in an on state. But whereas if device is in an off state, then IC will be 0. Current flowing through the device is 0. So if the current flowing through the device is 0, we can say that VCE is equal to VCC. So voltage across device terminals is equal to VCC. Means this, yes, our device is blocking this much of voltage. Our device is blocking this much of voltage. Okay. Now here, can we indicate this point? Can we indicate this point on this curve? You can check here on this plot. Can we indicate? It is IC0. IC0 means this is IC axis we are having. IC0 means here it is. Okay, definitely the point should lie on the VCE axis now. And what is the value of that? VCE is equal to VCC. So can we say that suppose if IC is 0, then yes, it is a VCE is equal to VCC. So what this indicates? It indicates that our device is blocking this much of voltage. Our device is blocking this much of voltage. You can check corresponding to this point, the voltage we have written it as a VCC. But what is the current? Current is 0 ampere. So current is 0 and voltage is high. So device is in an off state and device is blocking this much of voltage, right? Means you can check from 0 till VCC. Our device is in an off state only. Okay, device is in an off state only. So point to be noted. If we want to use the power BJT in power electronics, right? And if we are interested in keeping the power BJT in off state, then the power BJT should operate in which region? Cutoff region only. Na? You can check this point means what? It is in this region na? Below IB0 means this point we are having. So definitely, right? When power BJT is operating in cutoff region, it will act as an open switch. Point to be noted. They have asked the question, if power BJT as an open switch, if we want to operate, definitely our power BJT should operate in cutoff region only. Should operate in cutoff region only, right? So let me write here. Yes. So during cutoff region, cutoff region, yes, it is like switch or a BJT, or you can say the power BJT. Power BJT. Yes, it will behave as a open switch. Open switch. Is this clear? It will behave as an open switch. So this is the one thing. Now let us discuss about the closed switch. Okay, open switch we discussed. Closed switch, right? So closed switch means what? definitely this will act as a short circuit. So VC should be 0. So if we put VC 0 in this equation, if we put VC 0 in this equation, what will happen? Let me write. Yes. So if VCE is equal to 0 volt, right? If VCE is equal to 0 volt. So can we say that here in this equation, IC is equal to VCC divided by RL. IC is equal to VCC by RL. Now, where this point, yes, will be located on the plot, you can check here. VC is 0 volt and IC is equal to VCC by RL. So you can check here. Yes, IC means this axis. VC 0 means what? Yes, definitely the point should lie on the Y axis, that is the IC axis. Okay, and what is the value of that IC we have written? The value of IC is equal to VCC by RL. So definitely here that the point will be lying somewhat here, right? Let me write this as a VCC divided by RL, VCC by RL. So what this point indicates? This point indicates that voltage across device is 0, current flowing through the device is a high value. Means whether our device is in a on state or off state, our device is in a on state only. Yes or no? Voltage across device is 0 means what? It is acting as a short circuit, na? So that's why this point indicates device is in a on state. Device is in a on state, right? So let me write here. Yes. So this indicates. Now, yes, this point lies in which region? This point is, yes, it lies in which region? This is in a hard saturation region, na? Yes or no, right? So let me write. During hard saturation region, or in hard saturation region, you can write. Yes, power BJT acts as closed switch, right? Closed switch. Is this clear? Are you getting the point? Okay, so power BJT acts as a closed switch, right? Closed switch. They have asked the question, huh? So our power for as long as power electronic applications are considered, okay, because this is a switch and we are using it as a switch only, na? Power BJT it has a switch only. So in order to turn on the switch, we need to operate it in cutoff region. In order to turn on the switch, we need to operate it in hard saturation region. We need to operate it in hard saturation region. Okay. So now suppose if I draw a load line, okay, right? Then how it will be? So if I draw a load line, yes, suppose from here to here, let me draw the load line, right? So this indicates the load line. Now suppose when IB is 0, corresponding to this point, it is like a IB is 0, na? We have not applied the base current, we have not circulated the base current. So our device is in a cutoff region. So power BJT is in an off state. If I go on increasing the IB, it is like our operating point will shift from this point towards, yes, this your on state, that is a hard saturation region, right? IB 0 means operating point will be here. If I increase the IB by some value, some amount, then our operating point will switch into here at this point. So at this point means what? This point indicates the operating point is in active region. If I further increase the base current, the operating point will move further. Yes or no? If I further increase the base current, operating point will again move on the next curve. If I further increase, operating point will move here. And if I further increase the base current, operating point will move into the hard saturation region, right? So please try to understand, right? So here we are having based on the base current, we can change the mode of operation, okay, of the power BJT, mode of operation of a power BJT. For low base current, BJT will be in an off state. For high base current, BJT will be in an on state, right? BJT will be in an on state. Now you can check here corresponding to the cutoff region. Can we say that the voltage across device is high and current flowing through the device is very low? Corresponding to the cutoff region, the voltage across device is high and current flowing through the device is very less. So device is characterized with high voltage and less current. So what about the impedance? Impedance is also high. Okay, impedance is also high. right? So again, we are having the high voltage and less current. So during the cutoff region, what is the power loss in the device? Power loss in a device will be negligible, na? Because current is very less current flowing, even though the voltage is high, but current is a less current, na? Right? So this is a current only, right? This indicates your current. Okay. If the operating point is on this curve, I'm saying, right? Next. Now, if the operating point is in a hard saturation region, if the operating point is in a hard saturation region, can we say that the operating point in a hard saturation region, you can consider either this point, you can consider either this point, you can consider either this point, corresponding to the operating point in a hard saturation region. Yes, the device is characterized with a less voltage, na? Less voltage and high current. Very less voltage is there across the device and the current is high. So less voltage and high current means what? Again, the power loss will be very less, na? Right? So during the hard saturation region as well as during the cutoff region, yes, the power loss in a device is a very less. Power loss in a device is very less. But if you check the active region, you can check. Suppose, let me consider this point. Suppose this point we are having. Okay, this is the operating point, and this point is in active region, na? This point is in active region. Corresponding to this point, you can check the voltage value is also finite. Current value is also high, na? Corresponding to this point, we are having a current value here. Corresponding to this point, we are having a voltage across the devices at this point. So what is the power loss? Power loss is a high. Are you getting the point? Okay. So when device is in an active region, the power loss in a device will be high. So that's why for power electronic applications, okay, power BJT in active region, okay, is generally avoided. Because it causes the high power loss. So let me write here. Yes. During cutoff region, okay, device is characterized with a high voltage and small current. Ideally speaking, this current should be zero, but practical case we are having some leakage current. Okay, small current. So therefore, power loss in this cutoff region, okay, is a small. Right. Second thing, during hard saturation region, device is characterized with a low voltage and high current. So what is the product of these two? Again, power loss will be less, right? And this is what we expect now. When device is in on state, power loss should be less. When device is in off state, power loss should be less. And this is the advantage of power electronic switching devices, right? Next, during active region, yes, it is like a device is having a high voltage across the device and high current right? So what is the power loss? High power loss. So therefore, in power electronics, right? Therefore, in power electronics, active region operation in power electronics, active region operation of power BJT is avoided. Is this clear? Are you getting the point? Okay. Next. Yes. So the thing is, from here to here, we are increasing the base current, right? So let me indicate this also. IB4 is greater than IB3 is greater than IB2 is greater than IB1 is greater than IB, which is equal to 0, right? So this is the relation. Okay. So the difference between your signal level BJT and a power BJT, right? Important thing. In a signal level, generally you are operating it in active region, yes or no, right? But here we need to operate it as a switch only, na? So that's why here hard saturation region and cutoff region are preferred, right? We are avoiding the operation in a active region because it causes the high power loss, right? It causes the high power loss, right? Next, now let us discuss. Now suppose, yes, our device is operating. Now suppose our device is operating in the hard saturation region. Means I am circulating a high base current and our device is operating in a high saturation region. If I remove the gate current, if I remove the base current, then what will happen? Our device will again move towards the off state. So that's why the continuous base current is required. Continuous base current is required in this case. Okay. Next. So device operation totally depends on the base current, right? Device operation totally depends on the base current, right? So now let us discuss. Yes. Yes. Okay. So now let us discuss how much base current is required, okay, to turn on the device. How much base current is required to turn on the device, right? So next, how much base current is required to turn on device? So here, yes, we know base current is equal to IC by beta. Yes or no? We know in we are having in a transistor IC is equal to beta IB. Okay, so therefore I can write IC is equal to beta into IB. So this indicates IB is equal to IC upon beta. Okay, IC upon beta, right? So here, in order to reduce the base current, right? In order to reduce the, why I am interested in reducing the base current, because if we keep the base current value small, so it will reduce the what we can say, it will reduce the requirement of our base drive circuit. Okay, so for getting the less value of IB, we require a more value of beta. But as long as our power BJT is considered, in the power BJT we are having a thick layers na, compared to your signal levels. In a power electronics, whatever the device we are having a thick layer. In a signal level, you are having very thin layers. But whereas in a power devices, we are having a very thick layer. Due to the thick layer, the beta value, okay, of a power BJT is very less. Generally, it is in a range of 5 to 10. It is in a range of 5 to 10. But if you compare it with the signal devices, in a signal level devices, you are having the value of the beta, which is ranging from 80 to 120, na? Around 80 to 120. Okay. So here, let me write. Yes. To reduce base drive, I'm using here word base drive because the base current is there, na? Right? And base emitter is your controlling circuit. In the SCR, we're having a gate drive, right? That is a gate cathode. Here we're having a base drive. To reduce base drive circuit requirement, yes, IB should be kept low, right? Suppose for IB is equal to 5 milliampere, IB is equal to 5 milliampere. I want to turn on the device. Means if I circulate the IB is equal to 5 milliampere, okay, then our device will turn on. Our device will turn on. If I want to select, if I want to design our device in this way, okay, if IB is 5 milliampere, our device should turn on. Okay. So in order to get that 5 milliampere, yes, because 5 milliampere is comparatively very less current, na? So here required beta value will be more. Required beta value will be more. Okay. So to reduce IB, yes, beta should be more. Beta should be more. Because from this you can say beta is more, IB is less. Okay. So beta should be more. But if you check the difference between the signal level devices, okay, in signal level BJT, the value of beta in signal level BJT, beta is ranging from 80 to 120, which is a high, but whereas in power BJT, this beta is hardly in the range of 5 to 10, hardly in the range of 5 to 10, which is a very low. Now, with the help of this beta, can I get the less value of IB? Not possible, na? If beta is 5 to 10 we are having, then in order to turn on the device, we require more IB. Yes or no? Means we need to circulate more base current into the base drive circuit, right? So it increases the requirement of your base drive circuit. Okay, means we need to, if I want to circulate the more base current, then I need to connect the more value of ES in the base drive circuit. Yes or no? Right? Accordingly, your power losses in that RES register will increase. Na? RES register is there in the base and emitter circuit. Okay. So now why this beta is so less in a power BJT? Because let me write here. Beta in power BJT is less. Beta is less due to thick, yes, cross section of base layer, okay. So base layer is having a thick cross section. Definitely in power level devices we need to increase the cross section area. Why? Because our devices are having the more current rating, na, right? So that's why in order to make the devices to be a high current carrying devices, we need to increase the cross sectional area, right? And also we need to increase the width of that N minus layer also, right? In order to block the more voltage. Okay. So now let us discuss nowadays in real life, okay, how we are increasing this beta, right? In real life nowadays, how we are increasing this beta, because blindly we cannot accept this na 5 to 10. We need to do something to increase the value of beta. So for that we are using the Darlington pair. You might have heard in the analog electronics. Okay, we are having a Darlington pair. Okay, so what is the Darlington pair? Let us discuss. Okay, with the help of Darlington pair, we can increase the value of beta. We can increase the value of beta. So in Darlington pair, what we are doing? Yes. Darlington pair, right? So it is like we are having the we have connected the not SCRs, it is a transistors like this. Okay. So suppose this is our first transistor Q1. This is second transistor Q2. Okay. This is the emitter. Here it is a collector. Here it is a base of the first transistor. This is the emitter, base and collector of the second transistor, right? Let us consider this is a current IC. This is a current IC, right? Current flowing through our BJT. Okay. Now on which value this IC depends? You can check this circuit. Who decides the IC value? Who decides the IC value? Suppose when device is in on state, who decides this IC value? Load. Very good. Load. Good. Yes. The load will decide, na, REL means load register. The load will decide that IC value, na. That load may be anything. Suppose if I connected the DC motor here, okay. So DC motor is having some current rating. So when it is connected, it will draw some current, na. So that DC motor current is nothing but the IC if the load is DC motor. Suppose if the load is heating element, okay, if the load is heating element, right, then that IC will be like a current rating of that heating element, right? Accordingly, means IC is nothing but it is decided by the load, or you can say it is a load current. It is a load current. Okay. So next, so here we are having a IC. Next, let me write it as a, consider this current is a IC1. Okay, because this is a collector terminal. This is a IB1. This is a IE1. Okay, collector, base, and emitter. Next, let me write this as a IC2. This as a IB2, and here it is a IC2. Okay. Now here can we write IC is equal to IC1 plus IC2, right? IC is equal to IC1 plus IC2. Now what is the total, what is the collector current of our device? It is a IC. We are connecting the two BJTs in a Darlington pair, okay? Because one BJT is having a beta value very less. So in order to increase the beta value, I am adding one more BJT. I am connecting one more BJT. And the connections between the two BJTs are like this. Okay, that is the Darlington pair. Okay, so now for this circuit, if you check, the base current IB1 is nothing but the controlling circuit now for this controlling signal for this circuit. And what is the load current? Load current is a IC. Load current is a IC. Okay, now let us discuss how this circuit helps in improving the beta value. Right? So let me write IC is equal to IC1 plus IC2. IC is equal to IC1 plus IC2. Okay. So which is equal to, what is IC1? Can we write IC1 is equal to beta 1 into IB1? Yes, beta 1 into IB1 plus IC2. IC2, can we write it as IC2 is equal to beta 2 into IB2? Okay, so it is a beta 2 into IB2. Again, we can write it as beta 1 into IB1 plus beta 2 into IB2 means what? It is a IE1. IB2 means IE1. So let me write it as a IE1. So which is equal to beta 1 into IB1 plus beta 2 into IE1 we are having. What is IE1? That is the emitter current. Can we write this as equal to IC1 plus IB1? Right? IE1 means IC1 plus IB1. Okay. So it is a IC1 plus IE1. Okay. So now IC1 plus IB1. Right? IC1 plus IB1. Okay. Now further we can write it as which is equal to, yes, beta 1 into IB1 plus beta 2 into IB1 plus beta 2 into IC1. Okay. Now what is this IC1? Can I replace this IC1 with beta 1 into IB1? Yes or no? Right. So it is a beta 1 IB1 as it is plus beta 2 into IB1 as it is plus beta 2 is this as it is into, I am replacing this IC1 with a beta 1 into IB1. Now from this, can we take IB1 outside common? Yes. So we can write IC is equal to beta 1 plus beta 2 plus beta 1 into beta 2 into IB1. So what this indicates? You can check. IC means this correct current na? For overall circuitry, this is like a collector current IC. That is a load current, which is equal to IB1 means this is a base current we are having only. Okay. So this, can we say that this beta 1 plus beta 2 plus beta 1 beta 2 is nothing but the overall beta for this circuit? Are you getting the point? Okay. So overall beta for this circuit is nothing but this one, beta 1 plus beta 2 plus beta 1 beta 2. Okay. So let me write it as yes. So now okay. So now overall beta overall, okay, is equal to what? Beta 1 plus beta 2 plus beta 1 into beta 2. So now you can check, suppose each transistor is having a beta value equal to 10, because we know in a power transistors we are having a very less value of beta na, right? Suppose each transistor is having a beta value is 10. Okay, so suppose for beta 1 is equal to beta 2 is equal to 10. So what is the overall beta we'll be getting? So therefore beta overall is equal to 10 plus 10 plus 10 into 10, which is equal to what? It is a 120 na. So whether this is a high beta? Yes, this is a high value of beta. So nowadays we are using the Darlington pair in order to improve the beta value. In order to improve the beta value, what is the advantage of improving the beta value? Increasing the beta value. Increasing the beta value will reduce your base current requirement. Yes or no? Right? Means for a small base current also, I can turn on the device. For a small base current also, I can turn on the device. Is this clear? Are you getting the point? Right? So this is about the power BJT. So please keep it in mind. As long as the power BJT is considered, it is operated only in forward bias mode. It can be used as an off switch. It can be used as an on switch. Okay. Next, we cannot apply the reverse voltage across the BJT. In power electronics, I am saying, in a signal level, you can apply the reverse voltage, doesn't matter, because your voltage levels in a signal level are very less, na? But in power level, your voltage levels are very high. So if you apply the reverse voltage across the power BJT, your power BJT will get damaged. It will get destroyed. Okay. Next, we cannot apply the sinusoidal voltage. We cannot maintain the sinusoidal voltage across the collector and emitter terminals of the power BJT. Right. Next, power BJT is used in, yes, rectifier is not is used in DC to DC converters and inverter circuitries. Okay. Generally, the power BJTs, due to the thick cross section area, they are having less beta. So in order to increase the beta value, we are using the Darlington pair. Is this clear? Right? So this is about the power BJT. Right? I don't know, before this, whatever the page I wrote, I need to check. I'm using this, frankly speaking, I'm using this software first time. Okay. So, yes, I will check where that 10F has gone. Okay, I will check. Okay, in analog, you can apply the sine wave also, because in analog, whatever the sine wave you are having, you can check the voltage level and the sine wave voltage level in power electronics. There is a huge difference between the two. Okay, so that's why that high voltage we cannot apply here for power BJT, but in analog you can apply. Right? Now next thing is, yes, why the base value we are decreasing? The base value decreasing means, it is not, I am saying that some students are saying that if we decrease the base value, our device will turn off. Here our main task is to reduce the value of IB. So that means the required value of the base current for turning on the device. That is our discussion. Are you getting the point? Suppose if we don't use the power BJT, if we don't use the Darlington pair, then in that case, our IB required to turn on the device, it may be something in amperes, just like you can say 50 ampere, just like 60 ampere. We cannot circulate that much of current in a base circuit, na? That will cause increase in the losses. I'm saying without the Darlington pair, the required base current, suppose it is a 50 ampere, 60 ampere. But if we want to decrease that base current value, if we want to decrease that base current value, means what? Required base current to turn on the device. Required base current to turn on the device. So in that case, we need to use the Darlington pair. With the help of Darlington pair, we can improve the beta. And once we improve the beta, you can check now. Suppose we are having a load, it is having a current rating of, let us consider 100 ampere. For example, suppose we are having a load which is consisting of a current rating of 100 ampere. So without the Darlington pair, if this IC is 100 ampere, what value of IB is required to turn on the device? IB is equal to that 100 divided by, suppose beta is equal to 10. So 100 by 10 means 10 ampere you require na to turn on the device, and comparatively that value is very high. But now suppose same 100 ampere load we have connected, and now I am using the Darlington pair. So you can check here 100 ampere divided by with the help of Darlington pair, how much we are getting? 120 beta we are getting na. So it is 100 divided by 120. So what is the 100 by 120? You can check that current is comparatively very less na. So the meaning is required value of beta to turn on the device, we are decreasing. Are you getting the point? Okay. So this is about the power BJT. Yes. Because in a reverse bias, power BJT is having a very less voltage blocking capacity. The same thing we discussed here. You can check this one. This junction, when supply voltage is negative, means this junction is in a forward bias, and this junction is in a reverse bias na. And generally in application or generally in operation, the device, the junction which is in reverse bias na, that blocks the voltage, yes or no? And you can compare this junction J2, this side we are having a highly doped, heavily doped p-type material. Here it is a lightly doped p-type material. Both are having a very less thickness na. Both are having a very less thickness, right? So due to that, these layers will be having, okay, or whatever the depletion layer that will be present across junction J2, that depletion layer will be having a very less scope, very less space available to grow. So that's why here depletion layer cannot grow much. Okay, but here if this junction is in a reverse bias mode, definitely the depletion layer is having a space to grow na. So more space available to grow the depletion layer means depletion layer can block more voltage, right? So this is the thing. Next, so this is about the power BJT. Next, let us discuss. Okay. So next, let us discuss the power MOSFET. Okay, power MOSFET. So yes. So we know in a power MOSFET, we're having a depletion type, we're having an enhancement type, generally in MOSFET. Okay. So in a depletion type, we're having a P type, N type. In an enhancement type also, we're having a P type, N type. Okay. So we'll discuss which MOSFETs are preferred for switch applications. Okay. Switch applications. So let us discuss one by one. So first one. Yes. Suppose we're having N channel enhancement type MOSFET. So for N channel enhancement type MOSFET, we're having a transfer characteristic. This is like this. It is a VGS versus ID, right? Drain current, and the characteristic is like this. This is the first. Second one, we are having P channel enhancement type MOSFET. Okay. So same VGS versus ID, and it is having a characteristic like this. Okay. Next. Third one we are having okay. So N channel depletion type. So this is the VGS versus ID, and for this type we are having the characteristic like this. And last one, P channel depletion type. Transfer characteristic. Okay, so it will be like this. Okay, this type of characteristic, transfer characteristic we are having. VGS means what? For MOSFET, it is a, yes, VGS means what? For MOSFET, it is a controlling signal. Okay, because MOSFET is a voltage control device. BJT we discussed, that was a current controlled device, that was a fully controlled device. Okay, unipolar device and unidirectional device, right? Next, power MOSFET is a voltage control device. It is a voltage control device. Again, it is a fully controlled device only. Okay, we'll discuss why it is a fully controlled device and those things. Okay, so before that, in analog, you might have come across these four types. That is the N channel enhancement, P channel enhancement, N channel depletion, P channel depletion. So out of these four, which device or which devices are preferred as a switch in power electronics? How to decide? So for that, here we have drawn the transfer characteristics of each device. Okay, transfer characteristic of each device. So you can check, if we see, compare here P channel depletion type and N channel depletion type. Okay, in the P channel depletion type, if you check, if VGS is 0, VGS is 0, ID is a non-zero. What it indicates? VGS 0 means what? The gate signal is a 0. Oh, sorry, the controlling signal we have removed. VGS 0 means what? It is like we have removed the controlling signal. So now if we have removed the controlling signal, ideally, or what we expect, if the controlling signal is removed, the device should turn off now. But here what is happening in this P channel depletion type MOSFET, at VGS 0, yes, this much of current is flowing now, right? So can we say that here, if even though VGS is 0, the current flowing through the device, that is the drain current, is a non-zero, the meaning is device is in a on state. Okay, so generally this is not preferred. Why not preferred? Please listen it carefully. What we expect, if the controlling signal is removed, definitely our device should turn off na at all, right? If controlling signal is removed, device should turn off. But here what is happening? Yes, in this, from this characteristic, we can say that if VGS 0 means controlling signal is 0 or controlling signal is removed, controlling voltage is 0, then also our device is in a on state. Okay, so that's why we cannot use this as a switch. We cannot use this as a switch. Similarly, you can check this one, N channel depletion type. VGS 0, again here ID is non-zero now. So what this indicates? ID is a non-zero. Means what? Even though the controlling signal is 0, controlling voltage is 0, but our device current is a non-zero. The meaning is device is in on state only. And whether it is acceptable? No, we cannot accept this. Same, you can check the remaining two. Check for P channel enhancement type MOSFET. VGS 0, ID is 0. The meaning is, if we remove the gate to source voltage, if we remove the controlling voltage, our drain current has 0. Means what? Drain current 0 means what? Device is in a off state na. Just like a BJT. In BJT, we are having the collector current. Here we are having the drain current. Drain current 0 means device is in a off state. Okay. So if we remove the controlling signal, the device current is also 0, means device is in a off state, and this is what we expect now. Okay, means this can be preferred. Can be, I am saying. Similarly, you can check VGS 0 for the N channel enhancement. VG as 0, ID 0. Means when controlling signal is removed or controlling signal is 0, device is in the off state, right? So this is also acceptable. But now if we compare N channel enhancement and P channel enhancement, what is the difference between the two? In the N channel enhancement, we are having the current flow through the electrons only. Na? We are having only N type layer, N type channel, and through that the current is flowing. Next, definitely we'll be discussing in the next yes, coming slides. Okay, you will understand why I am saying that the current is flowing through the N channel only. And in the P channel, the current will flow through the P channel. Okay, in the P channel means what? In the operation, you might have come across in the analog electronics, there is a formation of layer, positive charges layer, na? And here it is a formation of negative charges layer. Okay, so here if you check the mobility of positive charges and the mobility of negative charges, which mobility will be more? Definitely the mobility of N channel will be more, na? Right? That is, the electrons mobility is comparatively higher than that of your holes mobility. Okay, so that's why generally the N channel is preferred. The advantage of this N channel, due to the mobility, as the mobility is high, means what? The electrons can pass through the semiconductor. When the electrons come across the electric field, okay, they can pass through the semiconductor material or through the metal, okay, at a short time compared to that of your holes, and due to that, what is happening? The device on state voltage drop will decrease. Okay, so here generally this is preferred comparative to that of your P channel. P channel is good. It is also giving 0. When we remove the gate signal, device will come to the off state. This is what expected. Okay, but here also we are having the same thing, na? But the mobility of the electrons is more compared to that of the mobility of the holes. So that's why generally this is preferred. If mobility is more, it is like your device will be having less forward voltage drop, right? So that's why it is a preferred. Okay, so now in power electronics, as a switch, which power MOSFET is preferred? N channel enhancement type MOSFET is preferred. Depletion types are not at all preferred. Okay, because they are having the, yes, characteristic like this. Means if we remove the controlling signal, device is not turning off. So what is the meaning of this? Means it is like our device is uncontrollable, right? Okay, so that's why these two are not preferred. Okay, so we are preferring only N channel enhancement type MOSFET. Okay, now let us discuss the N channel enhancement type power MOSFET. Okay, N channel enhancement type power MOSFET. Yes, N channel enhancement type power MOSFET. So let me draw. Yes, power MOSFET. The construction. Okay. This is the drain. The current is ID. Next, N plus layer, which is a comparatively thin. N minus layer, it is a comparatively thick layer. N plus diffusions. Okay. Right. So this is N minus, and here it is a P type layer. P type, or you can say P plus also, doesn't matter. So device is like this. This is a gate terminal. Here it is a metallization, that is a metallic contacts here we are having. And this is a source we are having, right? Let me indicate source here. Source here. Okay. Next, so this is the SiO2 layer. Silicon dioxide layer. It is a dielectric medium, right? Gate is not connected directly to the remaining structure. Here we are having the metal contact or the metallization, you can say. Metal contact. This is also metal contact. Okay, so this is a power MOSFET. Now we are having the layers like N plus, heavily doped N type layer, N minus. You can check this layer is the thickest layer. Okay, the purpose of this layer is to increase the voltage blocking capacity of the device. Next, we are having a moderately doped p-type layer, and here it is N plus, N plus, N plus, and N plus. We are having the diffused layers here. Okay, diffused small layers we are having. Okay, so three terminals are drain, gate, and source. Drain, gate, and source. Okay, and the symbol of the device is, it is like this. This is a gate, this is a source, and here it is a drain. Okay, so this is for a N channel. Okay, N channel enhancement type MOSFET, right? So between drain and source we'll be having the load circuitry, and between gate and source we'll be having the controlling circuitry. Okay, between gate and source controlling circuitry, between drain and source we'll be having the load circuitry. Okay, so now let us discuss the circuit operation. Okay, so now you can check here. Suppose gate to source terminal we have kept open. Okay, gate to source terminal we have kept open, means this between gate and source we have not connected any supply. Next, here we are having gate terminal is connected to the N plus, this P, N minus, P and N plus. Okay, means gate terminal is connected to N plus, P and N minus layer. But whether the gate terminal is directly connected, no. Gate terminal is connected through the SiO2 layer, through the SiO2 layer. Okay, SiO2 is nothing but the silicon dioxide layer. Okay, so silicon dioxide is a dielectric medium. It is like an insulating medium. It is like an insulating material. Okay, So as the insulation is present here, as the insulator is present here, so that's why even though we connect the source, okay, voltage source or the EMF across gate and source, those charges will not enter into the body of the MOSFET, enter into the structure of the MOSFET. Are you getting the point? Okay. So let us first assume that we have not connected any supply or any EMF between gate and source. Okay. Let us consider our device. Let us consider our device is in a forward bias mode. Our device is in a forward bias mode, and across the device we have connected a load. Okay, device is in a forward bias mode, and across device we have connected a load. Okay, so let me show here. Yes. So as I said, device is in a forward bias mode. So power MOSFET is in a forward bias mode. Forward bias. So what will happen? What will happen? So let me draw the circuit here. As I said, we have not connected source between gate and source terminal. Okay, G and S, we have not applied the any controlling voltage. Suppose this is a RL and we're having this is the voltage, right? So this type of circuit we're having, right? So this is plus minus. That is right. Let us consider it as a V. Yes, this is a drain D. REL. This voltage is VDS, right? And this voltage is VGS. MOSFET is a voltage controlled device. It is a fully controlled device. Okay. So now, if you check, yes, here we are having the circuit diagram. So from this, initially it is like our device is in an off state only. Positive potential will appear at the drain, right? Negative potential will appear at the source of the device, right? So drain is positive, source is at the lesser potential. Okay. So drain is at higher potential. So let me indicate here. Suppose drain is at a higher potential. Okay. And source is at a lesser potential, right? Drain is at higher potential, source is at a lesser potential. Means what? Across drain and source, we have connected a load and the supply voltage Vs. Is this clear? Right? So due to that, what happened? Drain is at a more potential, source is at a lesser potential. Okay. So same thing we have indicated here. So drain is at higher potential, source is at a lesser potential. Means can we say that from drain towards the source, the potential go on decreasing? Okay. So from drain to source, potential decreases. Okay. So now what will happen if you check here? Drain to source potentially decreasing. So whether this N plus N minus it forms a junction? No, it will not form a junction. Okay. This N minus and P, it will form a junction. Let us consider it as a junction J1, right? N minus and P, it will form a junction. Similarly, you can check P and N plus. This also, this will form a junction. Okay, this will form a junction. Let me write it as a junction J2. We're having Pn plus, Pn plus, Pn plus, Pn plus, but I am considering all these as a single junction type case. Okay, you can check, sir, here it is also we're having junction. Here also we're having junction P and N minus. Okay, so why we are not considering it as a J2 or J3? Okay, the thing is, if this is a N minus, this is P and P. If this is forward or reverse bias, definitely this will be a forward or reverse bias only, right? Same thing. So that's why I'm considering this full and this as a single junction type only. Okay. Next, let us discuss what is happening in the MOSFET. Drain is more positive, source is at a lesser potential. What will happen to the junction J1? Forward bias or reverse bias? Junction J1 reverse bias, because N type is at more potential than that of the P type. From drain to source, potential is decreasing. You can check where the source is connected, source is connected to this terminal. Here it is, means N minus P, N plus P, N plus. Here, next, N plus P and N plus, right? Here we are having the source connection. Source is not connected to this layer. Here we are having the gate connected. We are having the gate terminal connected. Means this one, are you getting? Whatever that green we have indicated, okay? That is like, again, it is like we have kept it as an open circuit type thing, okay? Source is actually connected to this layer, this part and this part. Source is not connected to the gate terminal. Please be careful. Okay. Next. So here junction J1 reverse bias, junction J2 forward bias. Okay. J1 reverse bias, J2 forward bias. So let me write it as J1 reverse bias, J2 forward bias. J1 reverse bias, J2 forward bias. Okay. So J2 is in a forward bias, so we don't have problem with the junction J2. The thing is junction J1 is in a reverse bias. Okay. So junction J1, if you check, for junction J1 at one side we're having a lightly doped layer na, and what is the thickness of that layer? The thickness of the layer is very high. It is the thickest layer na, right? So if we go on increasing the voltage between these, if we go on increasing this Vs, whether the width of the depletion layer across junction J1 is having a scope, is having a space available to grow, definitely it is having a space available to grow. Means what? Our device can successfully block, our device can successfully block that voltage. Are you getting the point? Okay. Means when a device is in gate to source signal we have not applied na, gate to source signal we have not applied means what? The controlling signal we have not applied. So definitely it is like our device should be in the off state only. So in the if the device is in off state, what we expect, device should block the voltage. Now how much voltage the device can block? It depends on the whatever the thickness of this n minus layer is there. So you can check here, we're having the thickness of the n minus layer is very high now, and for n minus layer is a part of the junction J1. N minus layer is a part of the junction J1. Okay, so that's why here you can check this depletion layer across junction J1 is having a space available to grow. Okay, so we can apply more voltage between drain and source. Definitely our junction J1 will block that voltage, right? So our device can block a high voltage, high forward voltage. Okay, so let me write, device can block high forward voltage. If device is blocking the high forward voltage, means operating point will be, if you check the static operating point locations, operating point should be on positive V axis na. The same thing we indicated, right, during the static operating point on VI plane for the power MOSFET. You can check. Okay, so device can block the voltage. Now how to turn on the device? Now let us discuss how to turn on this device. Okay, so in order to turn on the device, what we are going to do, we are going to apply the voltage Vs. We are going to apply the voltage VGS. Let me write it as this voltage is a VGS. Okay, we are going to apply the voltage VGS between gate and source terminals. Okay, between gate and source. So you can check here, gate is at higher potential compared to that of the source now. Are you getting the point? VGS, positive plate is connected to the gate, negative plate is connected to the source. So gate will be at a higher potential than that of the source, but potential at the gate will be definitely lesser than that of your drain potential. If you compare this Vs and this VGS magnitude is very less. Vs is your source voltage na, so that voltage is very high. Okay, so gate is at higher potential compared to the source. Gate is at a higher potential compared to the source. So now let me show. So gate is at a higher potential. So let us indicate here, gate is at a higher potential compared to the source. Means between gate and source, now we have connected the supply. Between gate and source, we have connected the supply. So now what will happen? Now you can check when device is in off state, that is when gate to source circuit, gate to source terminals we kept open circuit. Okay, due to that what happened? Yes, here we are having a depletion layer. Here we are having a depletion layer across junction J1. Okay, and the width of that depletion layer was increasing because junction J1 was in a reverse bias mode now, junction J2 was in a forward bias mode. Now if you check here, yes, gate is, if we apply the VGS positive, means gate is positive and source is negative. Whatever the voltage we connected between gate and source, the positive plate is connected to the gate terminal, negative plate is connected to the source terminal. You can check here whether the gate is directly connected, gate terminal is directly connected to the remaining structure of the device. No. So as soon as this positive plate of the supply is connected to the gate terminal, it is like the positive charges will be coming here, right? These positive charges will, yes, occupy this space or the, yes, space at this side. So similarly in this, what is happening, these positive charges which are coming from the positive plate of the VGS, these positive charges will occupy the space, yes, at this point. Are you getting the point? At the gate terminal, these positive charges will occupy the space. But definitely these positive charges will not enter into the device structure. Why? Because between gate and this structure we are having the SiO2 layer. So due to SiO2 layer means it is like your insulator, it is like your dielectric medium, right? So dielectric medium or the insulator is having a very high opposition to the current or to the flow of charges, na? So that's why our charges will not enter into the device structure. But what is the effect of this? You can check. Once the positive charges will occupy the space here, due to that, whatever the minority charge carriers are there, right? Whatever the minority charge carriers are there into this n minus layer, that is the positive charges, right? Sorry, whatever the, whatever the majority charge carriers, here we are having the positive, na? So definitely whatever the majority charge carriers are there in the n minus layer, okay, these majority charge carriers, what will happen? These will be getting attracted here, na? These will be getting attracted here, okay? So we'll be having, you can check here, these n minus will be getting attracted. So that's why here we'll be having the negative charges present. Similarly, you can check this, whatever the positive charges are, these positive charges at this side also we're having. So here you can check if the positive charges are here, whatever the minority charge carriers are present in the p-type layer, these minority charge carriers means electrons, these electrons will be getting attracted toward this side, na? Because here we're having a positive charges. So definitely the electrons from the p-type layer will be getting attracted toward this side, na? Because we know the force, we are having the attraction force of the attraction between the unlike charges, right? So that's why here negative charges will be coming here. Similarly, you can check this here also we're having the positive charges. So that's why whatever the minority charge carriers are present in the p-type layer, these will be getting attracted at this side. So you can check here, right? You can check here. Here we're having a n plus layer. Here it is a n minus layer, means it is like we're having the n type layer only. Here also we're having the n type layer. Now the problem was without the VGS, why the device was not switching into the conduction mode? Because of the junction J1. Junction J1 was in a reverse bias mode now. And when junction J1 was in a reverse bias mode, okay, it is like at this side we're having a layer of positive charges, okay. Now, but when the charges will be, negative charges will be getting attracted toward this side, so this full space, this full will be occupied by, yes, this full will be occupied by the negative charges only, na? So now you can check between drain and source, whatever the voltage we have applied, between drain and source, whatever the voltage we have applied, you can check here, current is expected to flow from drain towards the source, okay. So here if you check, once the electrons enters, okay, once the charges enters, whether the charges will complete their path, whether the charges will complete their path like this from n channel, that is from n type layers, through this n channel and through this n plus and again towards the source, yes, our charges can complete the path, again same, through these charges can complete the path and again reaches to the source terminal. Please be careful, this junction is already in the forward bias mode, so we don't have problem with this junction. We had a problem only with this junction J1, and in order to overcome that, what we have done, when the VGS is applied here, we will be having the positive charges layer, right? So due to that, negative charges will be getting attracted at this side, okay. So here we'll be having the n channel, that is the layer of negative charges, that is the inversion layer formation is there. So you can check here, it is a n type layer, here it is also n type layer, okay. So that's why our electrons can successfully complete their path, yes, from, yes, through these n channels, through this n, yes, n type layers, and again through this n channel. I'm saying this as a n channel. I'm saying this as a n channel, okay. So electrons can complete the path. We don't have problem with this junction, na? This junction is already in a forward bias mode, so we don't have any problem because its width was already decreasing and at certain point it will become 0. We had a problem with only this junction and this junction. that is junction J1 only. This is J1, definitely this is also J1. So for that we have provided this type of alternate path we have provided, right? Now my question is, if we increase the VGS, means here, if VGS is more, means what? This voltage magnitude VGS is increasing. So more the VGS, more positive charges will be here, na? So more positive charges here means definitely more positive charges will be here. So more positive charges here means what? Yes, more number of negative charges will be getting attracted here. Because higher the number of positive charges, higher will be the force of attraction, more will be the negative charges, those will be getting attracted towards this side, na? So more will be the width of the channel. So can I say that higher the VGS, higher will be the width of this channel? Yes or no? If we remove VGS, whether the channel will be formation, channel formation will be there? No. If I apply VGS, channel formation will be taking place. If I increase VGS, channel width increases. If I further increases VGS, channel width will be increasing. So can we say that more the VGS, because as the channel width increases, so it is like our charges can pass easily, na? More the channel width means what? Charges can pass fastly. Charges can move. Charges can pass. Charges can complete their path from drain to source easily. So more the VGS, higher will be the channel width, faster will be the charges rate of flow. So that's why more will be the current. So the relation is like VGS is more, channel width is more, faster will be the charges movement, and more will be the current. Okay, so important thing, VGS more, ID more. Okay, VGS is more, ID is more. Okay, is this clear? Next, so this is about when device is in a forward bias mode. Let us discuss, we'll take a break after some time. Okay, so let us discuss about when device is in a reverse bias mode, then what happens? When device is in a reverse bias mode, then what happens? Right? Yes. When device is in a reverse bias, or let me write that point first. Yeah. Yes. VGS increases, channel width increases, channel width increases means what? Yes, it will help for the movement of the charges. Okay, charges flow of charges, or you can say the movement of the charges. Okay, faster, and in addition ID will be more. Okay, so more VGS, more ID you will be getting. Okay, so that is the thing now. If VGS is 0, we expect that device should be in the off state, so channel is not formed, our device is blocking the voltage. This is what expected. If VGS increases, device should turn on, right? If VGS is greater than a particular value, na, right, then device should turn on. This is what we expect, na. And device is in on state means what? Current should be higher. Current should be higher. Okay, so more VGS, more will be the ID. So this is the thing when we apply the forward voltage. Okay. Now, if we maintain the reverse voltage across the device, what happens? If we maintain the reverse voltage across the device, what happens? Let us discuss. Yes, yes, yes. So if we increase, if we maintain the reverse voltage, what happens? Let us discuss. So for that, let me erase this first. Okay. So reverse voltage, if we apply, what happens? it is a n plus here it is also n plus we are having. Okay, so this type of structure we are having. Okay, so next, suppose if we apply the reverse voltage, means what? S is positive and drain is at negative potential. Okay, so between drain and source now I have maintained the reverse voltage. So it is like a source is positive, drain is negative. So source positive here, drain is negative here. So what happens? From source towards the drain, the potential go on decreasing. Okay, so from source to drain, potential decreases. So you can check here how many junctions we are having. We are having this junction and this is the second junction we are having, right? So yes, so in this case, which junction will be in a forward bias mode and which junction will be in a reverse bias mode? If source is positive, drain is negative, what our junction J1, forward or reverse bias? Source is connected here, source is not connected here. Please be careful. Source is connected to this part and this part only. So what about this junction? N plus P, forward or reverse bias? Yes, source is at a positive, drain is at a negative, means from source to drain potential decreasing. So junction J2, forward or reverse bias? Come on. Reverse bias, right? Junction J2, reverse bias, right? Junction J2 is in a reverse bias mode. What about junction J1? Forward bias, na? Because from source means this potential here and from here to here potentially decreasing. So P type is at higher potential compared to that of your N minus. So junction J1, forward bias. Now you can check. Junction J1 is forward bias. Junction J2 is reverse bias. Across junction J2 we are having, yes, P type material and N plus layer. And we are having only this much width, na? Right? So whether N minus layer is a part of the J2? No, N minus layer is not a part of the junction J2. Okay, N minus layer is a part of junction J1. And that junction J1 is already in the forward bias mode. Okay, so if I apply the reverse voltage across the MOSFET, what will happen? Our this reverse biased junction J2 cannot withstand with that high voltage and our device will get damaged. Are you getting the point? Because here the depletion layer is not having the much scope, right? The depletion layer is not having the much space available to grow, right? But whereas if in the previous case it was like a junction J1 forward by reverse bias, so that's why depletion layer had a more scope, more space available to grow. So that's why device was blocking more voltage. But here what happens? Our device will not block high voltage. Okay, so that's why in the MOSFET, if you recall in the MOSFET, okay, we show that static operating points on the VI plane, it is like only positive V axis, negative V axis. Yes, it was like we have not marked anything. Okay, because the for reverse voltage our device will get, it is like a device will not block that much of voltage and our device will get damaged. But if you apply the less voltage, definitely our device will block. Okay, but as long as power is considered, we're having the high voltages now, right? So that's why, yes, we here we are considering only high voltages, right? So let me write here. For reverse voltage, yes, junction J1 reverse bias and junction J2 forward bias. Okay, junction J1 reverse bias, junction J2 forward bias. Okay, so now junction J1 consists of very thin layers comparatively, I am saying. Okay, thin layers comparatively, and in that also N plus is heavily doped. Okay, so this layer, yes, cannot block high voltage because across this layer N minus layer was not there across this junction. Okay, N minus layer was not there. Okay, so thin layers only, so that's why high voltage cannot block, right? So next, okay, okay, so we'll take a break here. After the break, because it is 7:20. Okay, after the break we'll discuss about the output characteristics of the power MOSFET. Okay, then we'll be discussing about the remaining devices, right? Yes, do you want to speak something, Haripriya, Ramakrishna?
Sir, for reverse voltage, J2 is reverse bias, sir.
For reverse voltage,
J2 is reverse bias, sir.
is J2 is reverse? No, it is forward bias.
This is forward voltage, forward bias, no, sir. This is forward bias voltage.
Okay, okay. So here you are saying. Okay, J2 is reverse bias.
Yes, sir.
Okay, so what I have written?
Forward bias.
Sorry. Yes, yes, yes. So it should be here. Here it
That's
is
it,
a
sir.
forward and here it is reverse, right?
Yes, sir. That's it.
Okay, okay, okay. ठीक. Right. We'll start at 7:40. Okay. Right. Yes, I have corrected that, Shiva. Right. Okay. Okay. Right. So next, let us discuss the output characteristics of the power MOSFET. Right. So,
Sir, your video is minimized.
what?
Video is minimized. Sir.
Video is minimized.
It is okay, sir.
Now it is okay.
Okay, sir.
Okay. Okay. ठीक, ठीक. So output characteristics of power MOSFET. Right. So it is a plot between VDS, okay, versus ID. For various values of VGS, okay, for various values of VGS. So we're having the plot like this. Okay, so we're having the regions like this is like for, let me write it as a VGS 1, VGS 2, VGS 3, VGS 4, and VGS 5. Okay, so in that VGS 1 is less than VGS 2, is less than VGS 3, is less than VGS 4, and less than VGS 5. Okay, VGS 5, right? So we're having the regions like this is a cutoff region. Next, we are having the ohmic region. Here we don't have the saturation region. We are having the ohmic region. Okay, why it is a ohmic region? We'll discuss. Right. So this is the ohmic region. And this is the active region, right? This indicates the active region. Okay, so now here the cutoff region. So we're having if VGS is less than VGS TH, it is like device will be in the cutoff region, or the operating point will be in the cutoff region. Cutoff region. During cutoff region, device will act as an open switch. Device will act as an open switch. This is when VGS is less than VGS TH. Okay. Second, for active region, okay, for active region we are having VGS minus VGS TH. Okay, is less than VDS, then it is an active region. Active region means definitely your VGS is greater than threshold value. VGS TH means threshold value. Okay, so if VGS value is greater than VGS TH value and the difference between the two is less than VDS, then the operating point will be in the active region. Operating point will be in the active region. Next, if third one, let me write, VGS minus VGS-TH is greater than VDS, then the device will be in the ohmic region. Ohmic region, right? So we're having the three regions. One is the cutoff region, second one is the active region, third one is the ohmic region. If you check in the cutoff region, it is like a device is in an off state. Why it is in off state? Because you can check this is a cutoff region. Below this, whatever we are having, that is the cutoff region only. Okay. So in the cutoff region, the voltage across device is high. Current flowing through the device, you can check very less current. So current flowing through the device is very less. So that's why device will be acting as an open switch. Device will act as an open switch. Whereas if you check the ohmic region, in this region, ohmic region means this region we are having. Okay. In this region, the voltage across the device will be very small. Current flowing through the device is high. Yes or no? You can check any point in this region. It is like a current value will be high, voltage will be less. So that's why it is like device will be in the on state. So ohmic region means it is like a device is acting as an on switch or closed switch. You can say on switch or closed switch. Okay. And during the active region, what happens? During the active region, the voltage across any point you can consider, any point in the active region, you can consider you will be getting high voltage and high current only. So that's why the high power loss will be taking place, right? Are you getting the point? So let me write. Yes, during cutoff region, yes, voltage across device is high. Device is characterized with a high voltage and less current. So high voltage, small current means what? It is like a device is in a on state, off state or off switch, you can say. Second thing, for active region, during active region, yes, we are having high voltage and high current. High voltage and high current. You can check any operating point in the active region. Device is characterized with a high voltage and high current only. Okay. So it will be causing the high power loss. So generally, yes, this operating point in this region, okay, is not allowed for power applications. I am saying, okay, for power electronics applications, because in the power electronics we are having the high voltage rating, high voltage range and high current range. Okay, so if the voltage is high, current is also high, so power loss will be very high. Okay, so that's why it is not allowed. Next, during ohmic region. So ohmic region means during this region, the device will be equivalent to the on state resistance only. Why it is equivalent to on state resistance, we'll discuss. Okay, so it is characterized with a low voltage and high current. So it is like a on state of the device, or on state or on switch, you can see. They have asked the question, okay, power MOSFET in the operating point in the ohmic region. Okay, so device will be in the on state. Okay, cutoff region off state. Okay, and generally which operation is not operating point in which region is not allowed, that is the active region is not allowed, right? Let us discuss why I am saying it as a ohmic region. Why it is the ohmic region? Because if you check, yes, if you check in this case, yes, in this case, if we check here, when the channel is formed, okay, okay, so it is like current is flowing from this n type material. Here it is a n minus channel, n minus layer we are having. So most of the current, or when the current flows like this, so most of the part of the current is flowing through your n minus layer only, na? So you can check from drain to source, right? out of this path, which path n minus layers path is almost, it is equal to whatever the path of the drain to the source we are having. Okay, and n minus layer is a lightly doped layer. And what is the resistivity of the n minus layer? Resistivity of n minus layer is high now. So that's why when device conducts and the charges flows through this n minus layer only, most of the, okay, so that's why we are considering that device is equivalent to on state resistance, That's why you might have seen while calculating the conduction power loss, we have approximated, okay, we have replaced the on state of the MOSFET with its resistance only na, right? So that resistance is nothing but, yes, because the charges are flowing through the n minus layer, and the n minus layer's resistivity is high. So that's why the device is considered as an equivalent to the resistance or the on state resistance. So that's why it is a ohmic region. So we're having the ohmic region here, right? Next. So this is about the power MOSFET. Okay, power MOSFET. Next, let us discuss the next device we are having, that is the IGBT. IGBT stands for insulated gate bipolar transistor. Insulated gate bipolar transistor. Yes, definitely power devices are only for switches. Okay. So IGBT or insulated gate bipolar transistor. Yes. Now, if you compare, before this we discussed the two transistors. One is the MOSFET, second one is the BJT. Both are having some superiority and some drawbacks also. Just like if you consider the MOSFET is having the on state power loss comparatively more than that of the BJT. The same we have discussed by considering one numerical. Now we have discussed the one numerical where in the same numerical we considered one is the BJT and second one is the MOSFET, and we compared the on state power loss. So if you compare, the on state power loss of the MOSFET is high, on state power loss of the BJT is less. Second thing, the switching frequency of the MOSFET is high, switching frequency of the BJT is less. Okay, so it is like on state power loss of BJT is less, right? That is the good thing in the case of BJT, but BJT is having a less switching frequency, right? Due to the stored charges, okay, storage of the charges. Second thing, in the case of MOSFET, we are having a high switching frequency, but the drawback is at the second end we are having, it is having the high conduction loss. Okay, so these two devices are having some limitations. Okay, so in order to overcome this, we are having one new device, that is the IGBT, insulated gate bipolar transistor. Basically, it is the minority carrier device only. Okay, minority carrier device only, but it is having the switching frequency nearer to the MOSFET, somewhat lesser than that of the MOSFET, but it is nearer to the MOSFET. Okay, and MOSFET and this device both are having the PTC, positive temperature coefficient. Okay, the same thing we discussed, positive temperature coefficient. Okay, next. So now let us discuss the basic construction of the IGBT, insulated gate bipolar transistor. It is similar to that of your MOSFET only. The only one layer we have added here. Okay, so let us discuss. P plus layer, N plus layer, N minus layer, okay, comparatively the thickness of n minus layer will be more, right, compared to that of the other layers. Why? Because n plus here it is a n plus, and here it is a p plus over n. Okay. So this device is a combination of MOSFET and BJT. Okay, so that's why if you consider, if you check the terminals, okay, it is having a two terminals same as that of the BJT and one terminal as that of the MOSFET. Okay, so it is a terminals are collector, here it is a emitter, and next one is the gate, but gate terminal is not directly connected. It is through the SiO2 layer, right? This is SiO2 layer. So this is the gate terminal, right? So here it is a silicon dioxide, SiO2 layer. SiO2 layer, right? So this definitely this is also SiO2 layer. Okay, so we're having P plus N minus P plus and N plus layers. Okay, if you check the MOSFET, yes, you can check N plus N minus, okay, P plus N minus P and N plus layer was there na, okay, N plus N minus P and N plus, but whereas if you check here, same N plus N minus, instead of P here we are having the P plus and the N plus, the only layer added is nothing but this P plus layer. This is the P plus layer, this layer we have added. Okay, this layer is known as injection layer. This is known as a injection layer. This layer is basically to inject the minority charge carriers. Okay, to inject, or you can say that to introduce minority charge carriers. Minority charge carriers. Okay, next, the N plus layer is a buffer layer. This is a buffer layer. Some of the IGBTs you will find the N plus layer. Even some of the IGBTs, this N plus layer will be absent also. Okay, we'll discuss if the N plus layer is present, then how the IGBT behaves, and if N plus layer is absent, then what happens. Okay, that we'll discuss, right? Next, so now let us discuss the circuit operation. If you check, it is similar to that of the MOSFET only. The only thing is we have added here P plus layer. We have added here P plus layer. Okay, now let us discuss the first what is the effect of this buffer layer. What is the effect of this buffer layer? Okay, so suppose if we consider the buffer layer is present, okay, if N plus buffer is present, if N plus buffer is present, and second, let me write if N plus buffer is absent. Okay, if N plus buffer is absent, right? So in both cases, what will happen? Let us discuss, right? So here, so suppose N plus buffer is present. As I said, this is three terminal device: gate, emitter, and collector. Okay, gate, emitter, and collector. The symbol of the device is like this. It is a isolated gate, and remaining two terminals are same as that of the BJT. Okay, so this is the, yes, emitter, collector, and a gate. Between VGE, we are having the controlling voltage. between C and E, right? We are having the load circuitry. Between C and E, we are having the load circuitry, right? So now suppose the presence of N plus, right? And suppose our device is in a forward bias mode. Forward bias mode means what? Between collector and emitter, we have connected the load, okay, and the external supply, right? Between collector and emitter, external supply is connected and the load is also connected. So suppose we are having this type of structure. So here it is a REL, this thing, and suppose this we have kept open, na? Gate, emitter, this is a C and E, REL, and let me consider this as a VS, okay? So it is like a collector is at higher potential than that of the emitter, okay? So if the collector is at higher potential than that of the emitter, so what will happen? It is like a plus here, and here it is a minus, right? Plus here and minus here. So what will happen? P plus N plus, whether it forms the junction? Yes, it forms the junction, okay? So this junction, let us consider it as J1. So junction J1, forward bias or reverse bias? Definitely this junction will be in a forward bias mode. Whether N plus N minus forms the junction? No, it will not form the junction, right? N minus P plus, it forms the junction, okay? Let us consider this as the junction J2. Whether this junction will be in a forward or reverse bias? This junction will be in a reverse bias now, because from collector to emitter potential is decreasing. So N minus is at more potential compared to that of the P plus. So that's why junction J2 will be in a reverse bias mode. What about this P plus N plus, P plus N plus? This will be in a forward bias mode, okay? So let me write it as this as a junction J3, and this will be in a forward bias mode. Are you getting the point? So when collector is a positive, emitter is a negative, means IGBT is in a forward bias mode, junction J1 forward bias, junction J2 reverse bias, junction J3 forward bias, okay? So now due to that, what will happen? You can check junction J2 is in a reverse bias mode, okay? And across this junction, we are having at one side layer of N minus layer, lightly doped N type layer, and it is having a very high width, na? That is the thickest layer we are having. So due to that, this layer is having, or this junction is having, or the depletion layer is having the space available, right, to grow. So if we go on increasing the voltage, this layer blocks that voltage, right? So can we say that when the N plus layer presence is there, and if our IGBT is in a forward bias mode, then it blocks the forward voltage. Are you getting the point? It is blocking the forward voltage. Next, what will happen if the reverse voltage is applied? What will happen if the reverse voltage is applied? Reverse voltage means what? It is like now this is reversed. So collector is negative, emitter is positive, okay? So collector now negative, emitter positive. So here it is plus, and here it is a minus. Suppose here it is a minus, okay? So now what will happen? What about this N plus P plus junction? This junction reverse bias, na? Right? So this will be reverse bias. This one will be forward bias, and this one will be reverse bias, right? So let me write it as this is a reverse bias, this is a forward bias, and again this is a reverse bias. Now you can check junction J2 is in a forward bias, okay? Junction J2 is in a forward bias mode, and across junction J2 we are having a N minus layer at one side, but that junction is a forward bias mode, na? So that's why whatever the depletion layer present here across junction J2, its width definitely decreases, okay? So therefore our junction J2 will not block the reverse voltage. It is in a forward bias mode. The only thing is our junction J3 and junction J1 can block the reverse voltage, right? Reverse voltage means emitter positive, collector negative. So junction J1 can block and junction J3 can block the voltage, but you can check the widths of the junction J3, possible space available for the depletion layer to grow. You can check here, as these two are already heavily doped, N plus and P plus, right? And here the space available to grow for the depletion layer is very less, okay? So junction J3 will not block much voltage, right? Similarly, what about the junction J1? Junction J1 also both are heavily doped, right? And at the same time, the space available to grow for the depletion layer, reverse bias depletion layer, is also limited, na? Very less space available. So that's why whether junction J1 and junction J3 can block the high voltages? No. Are you getting the point? So here point to be noted, when the N plus layer, buffer layer is present, then IGBT can block only high forward voltage. Okay, but a small reverse voltage can block, right? IGBT can block a small reverse voltage, but high reverse voltage it can't block. It will not block. Are you getting the point, right? So let me write here. So if N plus buffer is present, then IGBT blocks high forward voltage, high forward voltage, right? High forward voltage, okay, and small reverse voltage, small reverse voltage. So it is blocking a high forward voltage and very less reverse voltage. Okay, so that's why it is known as the asymmetric IGBT. Asymmetric IGBT. Okay, because it is not blocking the high voltage at the forward as well as high voltage at the reverse. So that's why it is the asymmetric. Okay, but whereas if you check N plus buffer, if it is absent, then what will happen? Let us discuss. Okay, so and it is also known as the punch through IGBT. Punch through IGBT. This is the over and above information, right? Okay, next. If N plus buffer is absent, then what will happen? Let us discuss. Okay, so suppose if this N plus buffer is absent. Okay, so N plus buffer is absent means suppose if I remove this, what will happen? Right? So if I remove this and suppose here we are having, yes, it is like a minus here and here it is a plus, and suppose this is not present. Not present means what? This N minus and N plus will be same only, na? Okay. So let me remove this also. Okay, so now what will happen? It is like we are having only PN type of structure, right? Just like your SCR, na? P plus N minus P plus and N plus, this type of structure, SCR type structure. Okay, so collector is positive, emitter is negative. Collector is positive, emitter is negative. So what will happen? If collector is positive, emitter is negative, so it is like P plus N minus, forward bias or reverse bias? It is a forward bias. Okay, N minus P plus reverse bias, and P plus N plus, again it is a forward bias. So which junction or which depletion layer will block the voltage? Only junction J2 depletion layer will block the voltage. And across J2 you can check we are having the N minus layer, which is the thickest layer and a lightly doped layer. So that's why our depletion layer is having a space available to grow. So higher voltage we can apply, our depletion layer can block that voltage. Okay, means can we say that without the N plus layer, in the absence of N plus layer, our IGBT can block forward voltage? Yes or no? IGBT can block the forward voltage. Let us check for the reverse voltage. Let us check for the reverse voltage. Reverse voltage means here it is a plus, here it is a minus, right? So let us check for reverse voltage. What will happen? So this is a plus here, this is a minus here, right? So emitter to collector potential is decreasing. Okay, so N plus P plus, forward or reverse bias? You can check. This is reverse bias. What about J2 P plus N minus? It is a forward bias, na? And what about N minus P plus? It is a reverse bias, right? Reverse bias, because here to here potential is decreasing. N minus P plus, it is a reverse bias. Okay, so now you can check J3 reverse bias, but J2 is not having a much scope. J2 depletion layer is not having the, J3 depletion layer is not having the much scope to grow because of the limited space, as well as these two are heavily doped. Next, what about the J2? J2 is already in a forward bias. What about the J1? J1 is in a reverse bias. So J1 can block the high voltages, na? Because at J1 at one side we're having a N minus layer, right? So that's why J1 can block a high voltage. So you can check here. If the N plus layer is absent, then IGBT can block forward as well as reverse voltage. Forward as well as reverse voltage. Both are high voltages only. Okay, right? So let me write here. Yes, IGBT blocks high forward and high reverse voltage, right? High forward and reverse voltage, right? Next, so both are high, na? Forward also it is blocking the high voltage as well as reverse also blocking the high voltage. So it is a symmetric IGBT. Symmetric IGBT, and it is known as a non-punch through. Non-punch through. Okay, IGBT. Non-punch through IGBT. Is this clear? So this is the two types we are having. These are the two types. Please be careful. Now you can check here. For high power applications, can we say that asymmetric IGBT is a unipolar, but a symmetric IGBT is a bipolar? Huh? Please be careful. Asymmetric IGBT is a unipolar and symmetric IGBT is a bipolar. Okay. But suppose if they give you the question like, which of the following are the bipolar devices? And they will give the options like BJT, right? They will give the option like power MOSFET, right? For example, suppose third option, they will give something else. Okay. And the last option is like a IGBT. They suppose they have not specified like asymmetric or symmetric IGBT. Okay. Then please keep it in mind. We know na 100% BJT is a unipolar. Power MOSFET is also unipolar, right? So which device can be a bipolar? That is a symmetric IGBT, which is a part of the IGBT only, na? So that's why you can select the option as IGBT, na? Right? Are you getting the point? You can select the option as IGBT, right? So next, or let me write here. Symmetric IGBT is a bipolar device. Symmetric IGBT is bipolar device. And asymmetric IGBT is unipolar device, right? Unipolar device. You getting the point, right? Next, now suppose we're having the IGBT, this type, let us consider N plus here, na? We considered already N plus here, right? Next, how to turn on the IGBT? Yes, suppose it is a minus here and plus here. Suppose IGBT is in a forward bias mode. Okay, this type of structure we're having, it is in a forward bias mode. Okay, so now yes, P plus N plus forward bias. Okay, this is a reverse bias and this is a forward bias. Okay, so how to turn on the IGBT? IGBT is a voltage control device. Okay, and VGE voltage controls the IGBT. VGE voltage controls the IGBT, right? So suppose we're having, this is a reverse bias junction J2. At this side, we're having a layer of positive charges. Here it is a layer of negative charges. Okay, negative charges layer here, and here it is a layer of positive charges. Okay, so you can check, or let me indicate it as a layer of positive charges here. And next layer of negative charges. Right? So this is the actually reverse bias junction only I have drawn, right? Next, suppose VGE positive means here it is a positive plate of the supply connected, and here it is a negative of the negative plate of the supply, right? If VGE positive, you can check here. Current should flow from collector towards the emitter. Current should flow from collector towards the emitter. Okay. So now what will happen due to that? Yes, you can check if this is a plus, this is a minus, na? If this is plus here, this is a minus here. Okay. So due to that, what will happen? Here we are having the plus means at this side we are having the positive charges layer. Yes or no? Right? Positive charges will be taking or the occupying the space at this side of the gate terminal. But whether these positive charges will enter into the device? No, because we are having the SiO2 layer. Right? So due to that, what will happen? Yes, due to that, here we are having the positive charges means definitely whatever the negative charges are here, these negative charges will be, yes, getting attracted towards this positive. So that's why here we'll be having the negative charges. Okay. And these negative charges will be, yes, recombining with this. Okay. These negative charges will be getting recombining with this, and it will be, yes, forming the path like this. It will be forming the path like this. Okay. So that our devices can, our charges or our current can flow like this. Our current can complete the path from collector towards the emitter in this way, right? Similarly, at this side also we can see, because it is plus means definitely here it is plus, right? So in this side also our charges can enter or complete the path from collector towards the emitter, right? So higher the VGE, higher will be the width here you will be getting, just like a channel formation here also. Okay, channel formation here also, right? Next, so output characteristics of the device, let us discuss output characteristics. This is a plot between VCE, collector to emitter voltage, okay, with respect to your collector current, right? And for various values of VGE, for various values of VGE. So it will be like this. Okay, this is like a voltage blocking capacity of the device. Huh? Let me write it as Vs or V sustain. Means the voltage with which our device can sustain. Okay, our device can block this. Okay, next, we are having the three regions here also. Active region, saturation region. This is the saturation. This is a cutoff region. And this is the active region. From here to here, we are having the active region. Yes. These plots are for various values of VGE. For various values of VGE. Okay. So again, here also we are having, yes, if, or let me write on next page. Yes. Let me write it as VGE1, VGE2, VGE3, and VGE4. So let me write here VGE1 is less than VGE2 less than VGE3 less than VGE4. Okay. So if similar to that of the previous case only, yes, if VGE is less than VGE-TH, it is like our device will be in a cutoff region. Operating point will be in a cut-off region. So cutoff region means whether device will be in the on state or off state. Cutoff region means device will be in a on state or off state. Yes, device will be in the off state only, right? Same as that of the previous case, right? Okay. So device will be in the off state, or it will behave as a off switch. Off switch. Okay. So second, if VGE minus VGE-TH, VGE minus VGE-TH, okay, is less than VCE, okay, is less than VCE, then it is like a device is in an active region. Active region. So during the active region, the voltage and the current across device, okay, current flowing through the device, voltage across device will be high and high power loss. Okay. So high voltage and high current. High current. So that's why high power loss. High power loss, right? So generally it is not advisable. Okay. So not allowed. And third, we are having if VGE minus VGETH is greater than VCE. Okay, then it is like a saturation region. Saturation region. So saturation region means on state of the device or off state. It is an on switch, right? On switch or closed switch, right? On switch or closed switch. Is this clear? Right? So that's why you can check already whatever the switches we discussed. BJT, MOSFET, IGBT. In all the three cases, if we want the switch should be in the off state, then the operating point should be in the cutoff region. For on state, BJT, IGBT saturation region, and for MOSFET ohmic region. Okay, in all the three switches, if you check, generally the active region operation is not allowed. Okay, right? Because of the high power loss, right? Because of the high power loss. Okay, next. So this is about the IGBT, insulated gate bipolar transistor. Next, let us discuss the one more device. Yes, that is a GTO, gate turn off. Okay, we are having the GTO, that is a gate turn off. Before GTO, let us have some discussion on if I apply the negative gate current to the conventional thyristor, means our SCR, then what will happen? Let us first discuss that. Okay, so if conventional thyristor with the negative gate current, conventional thyristor with the negative gate current. Okay, what will happen? Let us discuss. Right. So we are having the conventional thyristor structure. Conventional thyristor means our SCR. Okay, it is a PNPN device. So structure is like this. P1 N1 minus P2 N2, or you can say P1 plus N1 minus P2 plus N2 plus, doesn't matter. Okay, next, three terminals are anode, cathode, and gate. Okay, anode, cathode, and gate. Okay, same structure I am redrawing. Okay, as a complete structure of the thyristor. Okay, so it is like this. This is a N plus, this is also N plus, and here it is a P, right? So we're having a gate here. Both the structures are same only. Gate, here it is a emitter, anode. And here it is a cathode. Okay, so cathode is N plus N plus N2, right? So that's what is N plus and N plus. Okay, so now suppose our SCR is in a on state. Suppose SCR is in a on state. Okay, and if I circulate the negative gate current, then what will happen? We already know when SCR turned on, after that we can remove the gate signal, right? Right. So now before that, one thing, because sometimes they ask the question, SCR is a dash dash type of device. Okay, and they give the options like some options, and in that the latching option will be there. Then always keep it in mind, SCR is a latching device. SCR is a latching device. Why? Because the latching phenomena means what? Let me tell you. Suppose we are having a device, once by applying the controlling signal, okay, and we have turned on the device, okay, means it is like device has latched in, okay, and after that if we remove the signal, if we remove the controlling signal, then also if our device continues into the on state, right, then that device is known as the latching device. Are you getting the point? I mean, just like your SCR, if I apply the gate signal, our SCR turns on, and if I remove the gate signal, our SCR will continue into the on state. Okay, so that's why that phenomena is nothing but the latching phenomena, and those devices are known as the latching devices. So SCR is a latching device. You can check BJT. BJT is not a latching device. Base current, if I maintain continuously, then and only then our device will continue into that particular state. Now, if I remove the gates, if I remove the base signal, if I remove the base current, our BJT again will turn off. Okay, so BJT is not a latching device. You can check for MOSFET, you can check for IGBTs. Okay, for these devices also the continuous signal is required. Continuous signal is required. Okay, next. So that's why these are the fully controlled switches we are having. Next, conventional thyristor with negative gate current. Let us discuss now. Same, we are having PN here. Same PN I have indicated here. Okay, anode means here it is anode. This is P1. So same here P1 you can consider, right? Cathode is N2. So here we are having cathode. It is N plus N plus. Okay. Next, P type layer, and here it is N minus layer. N minus layer is heavily doped. Okay, and gate you can check. Gate is connected to the P type layer. So gate is connected to the inner P type layer. Outer P type means here. Inner P type means here. Both are the same devices only. Both are the same devices. Now suppose SCR is in a conduction mode. SCR is in a conduction mode. We have already removed the gate signal back. Okay, and our SCR is continuously running in a conduction mode only. And if I circulate the gate current, if I circulate the negative gate current, then what will happen to the SCR? Let us discuss. Okay, so suppose current is initially flowing here in this direction, because SCR is in a conduction mode only, right? It is like all the junctions are in a acting as a short circuit. Yes or no? Depletion layer is not present here, right? Now, if I circulate the reverse gate current, right? If I circulate the reverse gate current means current IG is coming out from the device, Okay, so that indicates your negative gate current. This indicates the negative gate current. Okay, so it is like means we will be having a circuit here. It is like a resistor, and here it is a ES type of the thing, minus plus, and current is flowing in this direction. Current is flowing in this loop like this. Okay, so that's why you can check the higher potential will be appear at the cathode here, right? Let me write it as a plus, and comparatively lesser potential will appear at the gate. Okay, so you can check across gate and cathode we are having a P2 N2 layer. Across gate and cathode we are having a P2 N2 layer, and that layer N2 potential is higher, P2 potential is lesser. So can we say that this junction will behave as a reverse biaser now? Okay, but you can check this is limited. This current is gate current is flowing only in this loop, na? Gate current is flowing only in this part. Gate current is flowing only in this part. So only some portion of this N2 P2 layer, right, or this N2 P2 junction. Okay, some portion of, let me write J1, J2, J3. So some portion of junction J3 will behave as a reverse biased. Some portion of junction J3 will behave as a reverse biased. But remaining portion of the junction J3 will continue carrying the current, anode current as it is. Will continue carrying the anode current as it is. Please listen, I am repeating. SCR is in an on state, so that's why current is flowing from anode to cathode in the downward direction. If the negative gate current is circulated, then what will happen? It is like this N2 P2, that is the junction J3. Some part or some portion of this junction, means only this side portion, will behave as a reverse biased. But the remaining portion of this junction J3 will be continuing to the forward bias only. Because here anode to cathode we are having a high number of charges, those are flowing now, because current is high. anode current is comparatively very high than that of your gate current. Okay, so only some portion will be like a reverse biased, but gate current will continue into the on state. Gate current will continue into the high value, and that will be continuing from anode to cathode only, right? Continuing from anode to cathode. Okay, so it will not affect much on the operation of the conventional thyristor, on the operation of the conventional thyristor. The same thing we can represent here. Same thing we can represent here, right? Let us discuss how. Here, anode current is like this. This is your IA. Let me write it as IA. Okay, so this is the IA. This is the IA we are having. Next, same. Suppose gate current is negative, means this current we are having, it is a IG, which is coming out from the device structure, which is coming out from the device structure. So you can check here. Can we say that? Can we say that this portion of the device will be like a reverse bias, because gate current will flow here and again come back here now. So like this will be having the gate current. Similarly, in this case also you can check the gate current will be coming like this, right? So this type means from here, actually from here the gate current will be circulating. So this is a IG here, right? IG. But only this part of the junction, only this part of the junction will behave as a reverse bias. But whether the IA will continue from this type towards this side and from this side towards this side, yes or no? This is the IA. IA can flow like this. Okay, so in the conventional thyristor, keep it in mind, circulating the gate current will not affect on the operation of the conventional thyristor, because the thing is only your N2P, some part of the N2P2 layer, that is the junction J3, some part of the junction J3 will be in a reverse biased mode, but the remaining part, or the most of the part of the junction J3 will be continuing into the forward bias mode only, okay? So it will not affect much for the conventional thyristors, right? Next, so let me write, if negative gate current, yes
sir.
Yes please.
Sir, then how we can fire it? Fire that SCR means how we start it?
No. The
Like
thing is actually we are going to discuss the GTO, na? In the GTO,
yeah.
what we are going to do? GTO is
Means
like our SCR only.
Okay.
It can be turned on by using the positive gate signal. But
Okay,
if we
but
circulate the
we
negative
are
gate current,
controlling only, na?
Yes.
Gate terminal only for control the current.
Yes. So
then how we can means SCR have to start by some firing.
at the starting, if the SCR is in off state, we are going to turn it on by using the positive gate current only.
Yes, sir. Okay.
Now SCR is in on state, and we are checking that whether the circulation of the negative gate current will affect on the conventional SCR's operation, whether it is affecting or not, that we are discussing.
Okay.
And what we have discussed, that the reverse current, gate current or the negative gate current is not affecting much on the conventional thyristor's operation. Right?
Yes.
So with this, we are proceeding towards the GTO. Actually, our main motto is to discuss the GTO. But before GTO, we are discussing this concept. Okay? In the because we are having the conventional thyristor, that is the SCR, and the GTO. Both are almost same. Both are having the same characteristics. Okay? But the difference is GTO can be turned off by using the negative gate current. Okay? So in the GTO, what constructional modifications we have done? Okay, that you will after drawing the diagram you will understand. Okay, so next, so if negative gate current is circulated in conventional thyristor, here conventional thyristor means SCR. Conventional thyristor means SCR only. Okay, conventional thyristor. Then some part of or you can write some portion of J3 junction will be in reverse bias, okay, but anode current can continue from anode to cathode through remaining part of J3, okay. So here we need to consider first thing, note, assume conventional thyristor, that is SCR, is in on state, and we are circulating negative gate current. Are you getting the point? Negative gate current. So SCR is already in on state. This is important. Already SCR is in on state, and we are circulating the negative gate current, and we are checking that whether it will affect on the operation of the SCR or not, right? Means conventional thyristor, that is the SCR operation, right? Now let us have a discussion on the GTO, gate turn off. Okay, in the GTO, what modifications we have done, right? So gate turn off. So the structure of the GTO, again, it is similar to that of your SCR only. Some modifications we have done. We are having the P-type layer. Okay. Next, thickest N minus layer we are having. Next, we are having yes, this type of diffuser fingers, you can say N plus. Here it is also N plus. Here it is also N plus. Here it is also N plus. Okay. And next we are in the P type here. Right. So this forms the cathode. Okay. It is a N plus variable. Cathode. Here also N plus, this also forms the cathode. Okay. So all together, these four, it forms the cathode. So this is a cathode, right? Next, we are on the gate terminal. Gate is connected to the inner P-type layer, right? It forms a gate. Okay, so this type of structure we are having. This is the anode, right? So GTO, gate turn off. Already we have discussed about the symbol of the GTO, right? During the static VI characteristics of the static operating points locations, right? So structure, if you compare, here we are having the GTO, and whatever we discussed here, it is a SCR. If you compare Pn minus P as it is, okay, the thing is we are having the multiple cathode terminals here and multiple gate terminals, right? Comparatively here, if you check, only one gate terminal, and at N plus two sides we are having we had a cathode terminals. Okay, so due to that, what happened? Yes, this junction was a partially reverse bias, na? junction J3 was partially reverse biased, okay, due to the negative gate current circulation. But here what we have done, you can check, definitely GTO can be turned on same as that of your SCR, okay. GTO can be turned on by positive gate signal as that of SCR, as that of SCR. Are you getting the point, right? Same, even GTO is having the same characteristic as that of the SCR also, okay. Let us discuss for negative gate current what is happening in the GTO. For the negative gate current, what is happening in the GTO? So suppose GTO is already in a on state. By circulating the positive gate current, we have already turned it on, okay, as that of the SCR. You can check if here it is plus, here it is a minus, na, and if you circulate the positive gate current, right, whatever the reverse biased junction is there, okay. So these whatever the gate positive charges will be injecting from the gate current, these will be recombining, okay, these will be helping in reducing the width of the reverse biased junction, same as that of the SCR. Next thing, if the negative gate current is circulated, then what will happen? If the negative gate current is circulated, then what will happen? So negative gate current means, suppose here we are having the minus Ig. Suppose this is the minus Ig, means here we are having, this is a minus Ig, okay, that is the gate current is negative. So now gate current is coming out of the device structure, means definitely that will be negative only, okay. So it is coming out. So now the meaning is, from gate to cathode, it is like from gate to cathode, we have connected the supply. That is the ES, so that the positive plate of the ES will be connected to the cathode and negative will be connected to the gate terminal. Okay. So it is like, we'll be having, yes, between, or let me indicate here. Okay, this type of connection will be having plus here, minus here. So this plus will be at a cathode. So here it is plus, means here it is plus higher potential, here it is plus higher potential, here it is plus higher potential. Lower is at a gate terminal, lower is at a gate terminal. So that's why here it is a minus, here it is a minus, here it is a minus. So you can check this N plus and P na, N plus and P. This will be the reverse bias na, because cathode is at higher potential compared to that of the gate. So this N plus will be at a more potential than that of the P. So that's why this portion, okay, let me write it as gate current will be flowing like this. So this will be in a reverse bias mode. Similarly, you can check here it is plus, here it is minus na. Again, this terminal is of cathode only and this terminal is of gate only. So can we say that from cathode to gate current flowing na? Ig is flowing from cathode towards the gate, right? So that's why here again the cathode towards the gate means current is flowing like this, Ig. Similarly, here also cathode to gate current will be flowing. Here also cathode to gate current will be flowing. Here also cathode to gate current is flowing, and here also the cathode to gate current is flowing. Now you can check here. Can we say that this is a reverse bias? This junction na P, this is a P and N plus. So this is a reverse biased part. This is also reverse biased part. This is also reverse biased, reverse biased, reverse biased, and reverse biased. Now you can check that P and N plus. Here it is reverse bias, reverse bias, reverse bias, reverse bias. Same reverse bias and reverse bias here. So whether our anode current is getting the path to complete, okay, whether the anode current will complete its path from anode to cathode, right? It will not complete because this is like a reverse bias here, reverse bias here. But whereas if you compare in SCR, this portion was reverse bias, this portion was reverse bias. So still anode current had a chance like to complete the path from through this region. Na? But here whether it is a possible? No, not possible at all. Are you getting the point? Means what? We are completely blocking. We are completely blocking this side, means cathode side. We are completely blocking by circulating the negative gate current. So that's why the reason is when the negative gate current is circulated, the GTO turns off. So that's why GTO is a fully controlled switch. By circulating the positive gate current, it will turn on same as that of your conventional thyristor SCR. But if we circulate the negative gate current, yes, GTO will turn off. GTO will turn off. But if you already we discussed, if the negative gate current is circulated in a conventional thyristor, it was not affecting much on the operation of the conventional thyristor. because we had yes, some limited domain there for gate and the cathode, right? For that junction, or for that yes, for that junction. But here we are completely blocking this section. So that's why our current from anode to cathode, it will not flow, and our GTO will turn off. GTO will turn off. So let me write here. Yes. By circulating negative gate current, negative gate current, yes, GTO, yes, can be turned off, can be turned off, right? This is important. For negative gate current, GTO is turning off. Okay, so it is a fully controlled, it is a fully controlled device, right? Next, GTO operation during turn on is similar to that of, or same as that of, similar to that of SCR. Okay, because it is also PN device. You can check PN device we are having only. Okay, so same as that of the SCR, right? But the turning off is different. Next, GTO characteristics are same as that of SCR, same as that of SCR. Okay, so whatever the SCR characteristic we are having, same characteristic can be applied or can be used for a GTO also. So how the characteristics for SCR we are having? Yes, we are having it is like this. So this is a voltage across, let us consider GTO VA and current flowing through the GTO IA. Okay, so characteristic is like this. That is static VA characteristic. Okay. Same for different values of IG. Okay, different VBO will be getting. Right? VBO1, VBO2, VBO3, VBO4, right? Next, during the reverse bias also it is having the same characteristic as that of the SCR. VBR, okay, same GTO characteristic for different values of IG. IG1 you can say, IG2, IG3 and IG4, right? Okay, so this is about the GTO. Next, let us discuss the last device, TRIAC. TRIAC is equivalent to anti-parallel connection of two SCRs. It is like an anti-parallel connection of two SCRs. Okay, so symbol of a TRIAC. It is an anti-parallel connection of two SCRs, but be careful, it is having only one gate terminal, because both the gate terminals are connected together. So it is like a MT1, MT2, okay, or MT2, MT1 you can say. You can say it as a MT1, this as a MT2 also, doesn't matter, MT2, MT1, and this is a gate. And it is like having the circuit or equivalent to this type of this is a one, this is a second. Okay. So okay, and this can be shown at this side. It is like this. Two SCRs, okay, two SCRs connected in anti-parallel, but gate terminals of both the SCRs are connected together. Okay, gate terminals of both the SCRs are connected together. So it is like MT1, it is like a MT2. Here we cannot give the names like yes, this is a gate. We cannot give the terminal names as a anode and cathode, because what happens if you suppose if this is positive and this is negative, na? If this is positive, this is negative. It is like for this SCR, it is like a anode na here, and here it is a cathode, right? Similarly, for this SCR, here it is a anode and here it is a cathode. So you can check anode of one terminal is connected to the cathode of one second SCR. Na? Anode of one SCR is connected to the cathode of second SCR. So we cannot generalize the name to these terminals, right? So that's why it is a main terminal 1, main terminal 2, right? So when MT1 positive, MT2 negative, what will happen? It is like anode of the first SCR. Suppose this is the first SCR and this is the second SCR. Anode of the first SCR will be at a more positive than that of the cathode, and cathode of the second SCR will be at a higher potential than that of the anode. So can we say that if MT1 positive, MT2 negative, it is like this will be in a reverse bias mode and this will be in a forward bias mode? Yes or no, right? So if this is in a reverse bias mode, doesn't matter, but this will be in a forward bias mode now. And if we apply the gate signal, this SCR will continue or allow the current through from MT1 to the MT2, right? Similarly, suppose if this is positive, MT2 is positive and MT1 is negative, then what will happen? MT2 is positive and MT1 is negative. So this anode is at positive, this anode cathode compared to the cathode. So SCR2 will be more positive, SCR1 will be reverse biased, SCR2 will be forward bias, SCR1 will be reverse bias. Okay, so conduction will be through second SCR. Conduction will be through second SCR. Means this device can allow current in both the directions, that is from MT1 to MT2 as well as MT2 to MT1 also, right? MT1 to MT2, MT2 to MT1, right? So how is the characteristic, right? The characteristic will be like this. It is like anti-parallel connection of two SCRs. So let me write it as a voltage across device and current flowing through the device. Okay, so right. So for different gate current, same as that of your SCR. For different gate currents, it carries current in opposite direction only, direction also, right? Positive as well as negative, right? So this is the static wire characteristic of the triac. Static wire characteristic of a triac, right? So only introductory part we are having, as long as the triac or GT are considered, and for other switching devices also. Okay, we are having the in-depth analysis of the SCR, right? Okay, so this is about the first chapter, switching devices. We'll stop here. Tomorrow we'll start the second chapter, that is the rectifiers. Okay, rectifiers. So if you are having any doubts, please ask. Actually the thing is I have a time till 9:30 only, right? Because after 9:30 I have to complete the other tasks. Yes, please, one by one, if you are having doubts, please ask.
Good evening, sir.
Yeah, good evening.
Sir, in the conventional thyristor type with negative gate current is there, no, sir?
Conventional thyristor, yes, yes.
Uh,
yes.
Sir, it can act as a local hotspot, no, sir? Because of the some part is in not in conduction
where-
region.
Some part
Second-
here you are saying.
Hi, sir. J3 is some part is reverse bias and some is the forward bias. At the point of the forward bias can act as
most of the yes. Listen me. Only this part is reverse biased, very short. most of the part is already in a conduction mode.
Hi, sir.
So most of means from here to here, already this part is in a conduction mode. So already charges are flowing here, na? In a local
yes, yes, yes.
hotspot creation, generally what happens? Initially, it is like a depletion layer is present, and the depletion layer is blocking that voltage, right?
Hi, yes, sir.
When we circulate the gate current, then very small channel will be getting opened, na?
Yes, sir.
And due to
It is
that, most
large.
of the charge carriers will be passing through that small channel. So due to that, the local hotspot was created. But here what is happening, you can check already device is in a conduction mode, and this much of portion is already in a conduction mode, na?
Yes, sir.
So here we cannot say the local hotspot creation will be there, right?
How? Yes, sir. I got, sir.
Okay. Yes, one by one. Next.
Hello, sir.
Yes, please.
Sir, in MOSFET is voltage control device. Sir, voltage control.
Yes.
How we can say, sir?
Okay, just a minute. MOSFET, here we are having, this is a MOSFET.
Sir, GTO symbolic representation also.
Just a minute, let me complete this MOSFET thing. Yes. Yes, here it is, na?
Yes, sir.
Okay. You can check. Here we're having a formation of the depletion layer. No, sorry, depletion layer, not channel.
Okay.
And why this N channel has formed? Because of the VGS positive we applied.
Okay.
So due to these positive charges will come here. Due to the positive plate is connected na here. So
Yes,
positive
sir.
charges will come here. So at these positive charges, this P layer, negative charges, that is the minority charge carriers, will be getting attracted here.
Okay, sir.
So here also the same thing, negative.
Okay.
So we'll be having a formation of a channel here.
Sir, N minus
Now-
layer is releases what charges, sir?
Yes.
N minus layers, which charges releases, sir?
N
Positive or
minus is
negative?
already having the negative charge carriers. So we don't have any problem about this one. We had a problem about this path, na?
Okay.
So here actually the channel formation is taking place here and here.
Okay.
Now you can check if I increase the VGS,
Okay, sir.
whether the width of the channel will increase or decrease. Width means this vertical I am saying width.
Okay.
Width will be increasing or decreasing? Increasing.
Sir.
Because more the VGS, more will the positive charges will be here.
Can neutralize the charges.
Yes, attraction, force of attraction will be higher, more. That's why more number of negative charges will be getting attracted toward this side, na?
Okay, sir.
And you can check if VGS is zero. If VGS is zero, channel will not be formed at all.
Okay, sir. And
Right.
one more doubt, sir.
Yes.
Sir, in BJT, if AC supply is given to, then it will not work. I think damage.
Yes.
Sir, if any modification to get, if any modification are possible to get AC supplies given.
In BZT, actually, that we cannot modify, because you can check here. Huh? In BJT, what is happening during the reverse bias? Junction J1 is already forward bias. Junction
Okay.
J2 is reverse bias, na?
Yes, sir.
So suppose for blocking the reverse voltage, right? If I remove this N plus and if I keep it as N minus, and if I go on increasing the width of the channel, na, this layer,
Okay.
then it will affect, because as the layer N minus layer width increases means your resistivity is increasing.
Oh,
So how it will affect? It will affect when device will is in a conduction mode na. At that time, more forward voltage drop as well as the losses will be taking place.
okay, sir.
So that
Okay.
is the limitation.
Sir, symbolic representation of GTO.
Symbolic
Representation of GTO.
that we discussed at that time, but let me draw now also. Okay. You want the symbol na?
Yes, sir.
Yes. Let me draw here. The symbol of GTO is like this. Same here, anode, cathode, okay, and a gate. This is a gate. One is like this, okay. We are having
Okay.
three valid symbols.
Oh.
So second one is like this. One is for negative gate current. Second one is for positive gate current. This is the anode, cathode, and gate. Okay. This is the second symbol, and third symbol is like this. Let me draw here. So it will be like this. Both arrows on single line.
Okay, okay.
Right?
Thank you.
These three are the valid symbols of GTO.
Hello, sir.
Yes.
Sir, please open the MOSFET.
MOSFET.
Yes, sir. MOSFET. I had opted MOSFET.
Just a minute. Yes, MOSFET.
Sir, here the N plus layers are there at the ends.
N plus layers are there. In that.
Sir, in the middle two layer, we are considering in our operation, but what about the extreme two layers of N plus? Means what they do in operation?
You are saying what will happen to these N plus layers?
No, sir, that not the extreme two layers. Sir.
This one, this side.
Yes, sir. Yes, sir. Yes, sir. These two
Okay,
layers.
okay.
What is their operation?
No, the actual thing is conduction will be taking through this only. Why? Because you can check this junction was in a reverse bias mode, na?
Yes, sir.
So if this is reverse bias mode, means this junction was actually blocking the voltage, na? Means it was not allowing the charges to flow. So for
Yes.
that we have created this path with the help of this VGS. So current will be flowing like this. But once the current starts flowing, so it is
Yes.
like whatever this reverse bias junction was there, na?
Yes, sir.
Right? So that junction's depletion layer width will be automatically getting decreasing because one charger starts moving now, right?
Yes, sir.
So automatically this will be getting neutralized because you can check at this side we're having a layer of positive charges, and through this we're having electrons will be moving.
Yes, sir.
So that's why the some charges will be getting neutralized with whatever the positive will be here. And after that, this is at the start only. Okay. After some time, it will be like a current will be flowing through this also like this. Okay.
Yes, sir. Sir, is there any local hotspots created here?
Here, no. We don't have the concept like a local hotspot in this MOSFET, power MOSFET.
Okay, sir. Sir, I am
Right.
asking about the extreme to N plus layers, sir. This is okay, sir. The conduction is occurring from the middle layers of, but what about the extreme two layers of N plus?
No, that is what I am saying. Initially, your conduction will be like this from here to these inner two N plus layers.
Yes, sir. Yes.
But once the current starts flowing now, automatically the width of this depletion layer,
Yes, sir.
which was in a reverse bias mode, right?
Yes,
That depletion layer also after some time it will get vanishes, and after that the current will be flowing like this also, because you can check this N plus is again connected to your source now.
Yes, sir.
This N plus is also connected to the source.
Yes, sir.
So you can check in the SCR also what happened in the SCR. When SCR is in a forward bias mode, junction J2 was in a reverse bias mode.
Yes, sir.
At that time, what we did, we injected the positive charge carriers into inner P type layer.
Yes.
So some only very small portion, only very small channel was opened there.
Yes, sir.
So first conduction was from that small channel. But after some time, what happened? All that remaining, whatever the junction J2 portion was there, that was blocking the current or blocking the current, right?
Yes, sir.
So that automatically we will be getting, you can say, vanished.
Okay, sir, we
Same-
can
same
take
will happen, right?
sir, can we take the instead of 2 layers of n plus, we can completely join it
Instead of taking,
2 layers of n plus. So we
Okay.
can completely join and make a 1 layer.
then
onto
it will affect on your device current carrying capacity actually.
Yes.
Because if you check, if you remove these contacts now, actually here
Yes.
what is happening, current is diverting from this point, it is having the two possible ways now, and whatever the
Yes.
current here, if you check, once this depletion layer will be vanished, after that
Yes.
current is getting divided now.
Yes, sir.
So that's why your overall current carrying capacity of the device will be more. If you reduce it, we'll be having the limitation in the current carrying capacity.
No, sir, not to reduce it,
Yes.
but to make a complete channel instead of this 2 at one side. We have taken n plus, and
If
here
you are
extend
saying full
n
n
plus.
plus channel here,
Yes, sir. Yes, sir. Yes. Full
then
n plus and
okay, full n plus means it is like n plus p, and here again n type material, na?
yes,
So
sir.
that will be like your BZT, it will be acting.
Sir, అది అడుగుతాను.
NPN type nothing.
Yes, sir. NPL.
Same as of BZT, that will be happening, right?
Yes, sir. Okay, sir.
Sir, hello, sir.
On what
Good.
sir,
Yes, yes, please one by one.
sir, on what factors the switching frequency of device depends upon, sir?
On what factors?
The switching frequency of the device depends on.
Switching frequency of the device depends on, we discussed that thing, charge storage hai na, right?
Yes, sir.
On that factor it depends. If you check in a minority charge carrier devices, what is happening due to the conductivity modulation, right?
Yes, sir.
The charges will be getting added into the n minus layer. So
Yes, sir.
conductivity of the n minus layer will be improving, na?
Yes, sir.
So it is like n minus layer was storing the charges.
Yes, sir.
So due to that, to remove those charges, we require some time, our devices.
Yes, sir.
So that's why it is having some TRR and TGR concept, right?
Yes, sir.
Yes, yes. The same thing was there. But here you can check, here conductivity modulation is not there,
Yes, sir. Yes, sir.
right? So,
Sir, and why power BJT is modeled as a voltage source and a on-state resistance?
why power BZT is modeled as a voltage source? Okay, okay. Yes, here it is. Power BZT. Yes. During the on state, right?
Yes,
So
sir.
you can
On-state.
check here, you can check here in the power BZT, what is happening during this hard saturation region. It is like our device will be in the on state, na? And the operating point will be here or somewhere here. Okay, you can check nearly your voltage drop across the device is nearly same.
Yes,
So
sir.
that's why we are representing it as a constant voltage source.
Okay, sir.
Right? Okay.
Sir, it is a combination of voltage source and on-state resistance, you said, sir.
In BZT, it is a not combination. In BZT, is it a constant voltage source?
Oh, okay, sir.
But in in a MOSFET, it is only resistor. And for other devices, right, we're having a combination. You can check the voltage. Okay, next.
Hello, sir.
Please faster, please a bit faster.
Hello, sir.
Yes, please. One by one, come on.
Sir, hello, sir.
Yes, please.
Sir, in piecewise modeling of switch during on-state, you said MOSFET has to be represented with resistor, no, sir, instead of switch.
Yes, yes.
But here during forward bias of MOSFET, next slide, sir. Can you open?
This slide, no?
Next slide, sir. Next one, sir, 17F.
This slide?
Sir, you drawn one diagram, no, sir, MOSFET during forward bias.
Just a minute. MOSFET during forward bias.
Yes.
This one? No.
Okay, sir, I will ask, sir.
Okay, please ask.
We have to apply the gate signal between VGS, no, sir.
Not gate signal, it is the voltage, VGS voltage, yes.
VGS voltage means then we have to represent the MOSFET during on-state with voltage source, no, sir. Then in
No, it is not like that. Whether the device behaves as a voltage source or a combination of voltage source and resistor or only resistor, okay, piecewise modeling, we discussed, it
Yes, sir.
doesn't depend on your controlling signal. Right, controlling signal is only to turn on the device, right? But here you can check in the MOSFET what is happening when device is in a on state, right? Whatever the charges are flowing, most of the charges are flowing through the n minus layer only. Now most of the path is through n minus layer only, and that n minus layer is having a high resistivity. So equivalently we are considering that our device during on state is behaving as a resistor only, on state resistor, right?
Okay. Sir, this N minus layer will have high resistivity, sir.
Yes, lesser the doping density, more the resistivity. Always keep it in mind.
Okay, sir. Sir, one more doubt, sir. One more doubt, sir.
Yes.
Sir, what is the difference between normal thyristor and detailed thyristor, sir?
Normal thyristor and
Detailed thyristor, sir.
who told you detailed thyristor and normal thyristor?
Sir, actually we are having labs, sir. We are doing MATLAB. In that we have took a detailed thyristor, sir, and we have done connections.
No, that during the MATLAB simulation, detailed thyristor means what? If you click on that, you might be seeing various parameters we need to put there.
Yes,
that is
sir.
a latching current, something, right?
Holding,
Holding
yes,
current,
sir.
right? On state
Yes, sir.
resistance, maybe that software might be asking, right? So that is
Yes.
like your detailed thyristor, and only thyristor means most of the parameters they have generalized. Okay. Only
Okay, sir.
few,
They
that
are
is
specific.
voltage rating and current rating, they might be that software will be asking you. Okay.
Okay, sir.
Okay.
Hello,
Okay,
sir.
Yes, please.
6F, sir.
6F, na?
Yes, sir.
Okay. Yes.
Sir, active region, what region we want to consider, sir?
Active region means, yes, you can check here.
Can
From
you
this
please share
dotted
it?
portion
Okay, sir.
till this instant.
Okay, sir.
Okay, from dotted portion to this till this instant, that is active region.
Up to here, below which level, sir? Means you draw the one load point, no, sir.
Which node point? The here, no?
Load line, sir.
Yeah, load line. Okay,
There
means
you.
on load line you want, na?
Yes,
So
sir.
on load line, it is like from this point to this point. This
From
is
that
active
point.
region.
Sir, you told once, no, sir. If you are considering the second point,
Second means here.
yes, sir. You are telling that it is in the active region.
I am telling that it is in a
Active region.
no. Actually, the thing is, you can check. This plot is for IB 0 ampere.
Yes, sir.
So IB 0 means it is like your device is in a off state.
Yes, sir.
So whatever the points you are having on this curve, all are in a cutoff region only.
Okay, sir.
After this, whatever point here it is, you can say, okay.
Okay,
All
sir.
these will be your active region points,
Okay, sir.
right?
Okay,
This-
after.
including this curve and below this, we are having a
Okay.
cutoff region. Right?
Okay, sir. Okay. In 26F, 10F, sir.
10F. Okay.
Sir, gate drive circuit, you told one point, no, sir. 9F.
Base drive, no?
Base drive circuit, sir. Can you explain
Yes,
that one, sir?
Okay, means you are saying that why beta overall should be high here.
Yes, sir. Just to simply.
How it is affecting on the IB.
Yes, sir.
Right? So please listen.
Okay. Sir.
Yes, we used a Darlington pair, right?
Yes, sir.
Okay, so I don't know where it has gone. Okay, let it be. Okay. So without Darlington pair, what is the beta value our transistor is having? It is hardly 5 to 10.
Okay. Yes, sir.
Right? So
Yes,
suppose I am using a DC motor, for example.
Okay, sir.
That DC motor is connected as a load to the transistor. Okay, in a transistor circuit, we are having supply we're having a DC motor, and to the collector terminal of the transistor, we have connected the DC motor's one terminal, and DC
Yes.
motor second terminal is connected to the positive plate of the supply, right?
I see.
So it is like we're having transistor which is acting as a switch. Okay.
Yes,
Suppose
sir.
that DC motor is having a current rating of, let us consider 100 ampere.
I see.
Okay. So if that current rating of the DC motor is 100 ampere, the meaning is our collector current, when the switch is in on state now, at that
Yes, sir.
time, the collector current is nothing but the DC motor current.
Load. Yes, sir.
So that is equal to 100 ampere collector current.
Yes, sir.
So if your collector current is 100, collector current is to be 100 ampere. Okay. And our
Yes.
BJT is having a hardly 5 to 10 beta value.
Yes, sir.
Right. So suppose it is a 10, at max consider it as a 10. Okay.
10.
So if beta is 10, IC is 100. So what value of IB we require? IB should be
20.
equal to 100 divided by IC by beta, na IB means. So
20.
it is 100 divided by 10 means 10 ampere IB we
see.
require. Sorry. Yes, 10 ampere IB we require. The meaning is when I circulate the 10 ampere IB, then I will be getting IC is equal to 100 ampere means our device will be in the on state.
Yes, sir.
So now the meaning is in order to turn on the device, we require 10 ampere to be circulated in the base drive circuit.
Yes, sir.
So if we circulate 10 ampere in a base drive circuit, what is the power loss of that circuit? That will be high, na?
Yes, sir.
So in order, and whether your controlling signal in the range of 10 ampere, it is a very high value actually. We cannot accept that. So in order to reduce that value, okay, we are using the Darlington pair.
Okay.
In the
Base drive
Darlington
circuit.
pair, we consider the beta overall is equal to what? Beta 1 plus beta 2 plus beta 1 beta 2.
I
So
see.
if we increase the overall beta, suppose for the same 100 ampere, now my beta is, let us consider 100.
Yes, sir.
So for same 100 ampere, my beta is 100. So 100 IC divided by 100 beta, right?
One.
It's like 100 by 100 is beta value required, IB value required is now 1 ampere.
Yes, sir.
The meaning is if I circulate 1 ampere, na,
Yes, sir.
then my device will turn on.
Yeah.
The meaning
Sir.
is means the required value of the base current to turn on the device, we are reducing it.
Okay. That is the base drive circuit means.
Yeah, that is the base for the base drive circuit, right?
Okay, got it, sir. 26F, sir.
26F.
Sir, here also you told one point here, sir. If you remove the IB current means then it will automatically turn off.
Yes. If you remove
Why
the
it
IB
is-
current, na, yes,
Yes, sir.
yes, please.
Why it is happening, sir? Why it is turning off, sir? That I didn't get that
Because you
point.
can check in the BJT structure, you can check. Yes, that was like 16, na?
Yes, sir.
No.
1, 6, sir.
Yes, in this structure, if you check, if I remove this base drive, okay,
Yes, sir.
comparatively
sir.
we are having very thin layers here, and these are
Yes.
heavily doped. If I
Yes.
remove it, this junction will be again switching into the reverse bias case, right?
Okay. Sir, in
So that is-
SCR it is not happening, no, sir. Why here it is happening, sir?
In the SCR, it is happening because in the SCR we're having 3 junctions there.
Yes, sir.
Here we're having only 2 junctions.
2 junctions.
So that's why if you check already 2 junctions, we are already in a forward bias mode.
Yes,
Here the
sir.
thing is we're having 2 junction and one is forward bias, second one is reverse bias.
Yes, sir.
Right? So that is overall force in SCR will be more. You can check.
Okay, overall forward biasing
Yes,
condition.
yes, yes. Okay.
Okay. Okay. 26F, sir.
26F, yes.
Sir, here some partial reason is there, no, sir, for the flow of current from P to anode to cathode.
Some partial region.
Extreme right and extreme left.
Yeah,
there
that you can say, but comparatively, what is the width of this? It is a very less, na?
Yes, sir.
So that's why your comparatively current will be also very less, and you can say that that as the reverse leakage current also.
Sir, but how can we say that it is turning off, sir? Gate can be turned on by positive and signal as that.
This is a negative gate current we are circulating.
Yes,
And
sir.
what was, yes, because from here you can say cathode here, gate here. I have shown only one here gate current. You can
yes,
check the number of charges will be passing like this na here.
yes, sir.
It's like it will be blocking this full portion. It will be blocking this full portion. Like this here also full blocking, right? Same thing. The only thing is, as you are saying, only this part will be, some narrow part will be through that possible the current can flow. Here also through the narrow path the current can flow. Okay.
Yes, yes.
But that path is very less comparatively.
Okay, sir.
Right. Okay.
Okay, sir.
Hello, sir. Hello.
Yes, please.
Sir, one basic question, sir. Sir, for getting the.
Will you please speak a bit louder?
Sir, one basic question, sir. Can we
Yes,
sir?
please.
Sir, to get a conduction of what we say junction, you say that when the current is passing through, sir, P plus to N minus, then it is a forward bias, and if you N to P, then it is a reverse bias junction, sir.
When the current is not passing, when the potential at P plus is more and N plus is lesser.
Sir, how it is? I am not getting, sir.
Miss,
On what basis, sir?
Okay. Please listen here.
Yes, sir.
Suppose, yes, let me show you one device so that you will understand better. Suppose this device we are having, okay?
Yes, sir.
Now we are having 3 junctions. That is fine.
Yes, sir. Yes.
Okay. Suppose I maintain the forward voltage across anode and cathode.
Yes, sir.
So anode is more positive, cathode is lesser potential.
Yes, sir.
Right?
Yes, sir.
So anode is at higher potential, cathode is lesser, means what you can check. Here we are having a device, right? It consists of the 4 layers and 3 junctions. Out of that, upper side a higher potential, lower side lesser potential. So can we say that this full potential difference is appearing across the device structure only?
Yes, sir.
So, but anode is more positive than that of the cathode. So can we say that from anode to cathode potential is decreasing?
Yes, sir. Yes.
For example, suppose here I have connected the positive plate of the 5 volt voltage source to my right hand. Negative plate of the 5 volt voltage source I have connected to my left hand. Okay.
Yes. Yes.
So what is the total potential difference across my this part, that is the yes, across my body? Let us consider 5 volt.
Zero.
So you can consider if I say that the my left hand potential is 0 volt. So what is my potential at the right hand? 5 volt.
5 volt. Okay, sir.
So the potential difference to be 5 volt, na?
Yes,
so
sir.
if
Yes.
this is 0 volt, therefore this is a 5 volt.
5 volt. Okay, sir.
So here 5 minus 0, so that's why this potential difference is 5 volt, na? So
Yes,
now
sir.
from 5, what is happening? If this is a 5 volt, na, at
Yes, sir.
somewhat middle, the potential will be less than the 5 volt.
Yes.
As I approaches towards these fingers, na, left hand, okay,
Yes, sir.
the potential will be decreasing.
Yes, sir.
So
Yes.
same is happening here. You can say from here to here the potential is decreasing. Okay, so it is like whatever the potential here, the higher potential will be at the P1 type, P type layer,
Yes.
P1 type, upper
Yes.
P type.
Yes.
Before compared to that lesser potential N1 minus,
Yes. Yes.
compared to that P2 lesser potential, N2 lesser potential.
Yes, sir.
So P1 is at higher potential than that of the N1 minus. So junction J1 forward bias.
Forward bias. Yes, sir.
N1 is at higher potential than that of the P2. So junction J2 reverse bias.
Sir,
N
means-
type is at higher potential, na?
Yes, it means always current flowing from P2 to N2. P2
Current is
N.
always flowing from.
P2 N.
Don't consider it in terms of current. Actually, it is in terms of potential.
Okay, okay, sir.
Simple thing. You can remember that diode thing. Diode is a PN junction, na?
Yes, anode to cathode.
Yes. Same here we are happening. Yes, if P type material is at a higher potential, N type is at lower potential. Diode, we say that it is in forward bias mode, na?
Yes, yes.
So
Yes.
if P type positive, N type lesser
Negative.
potential means then forward positive.
N is equal
Forward
to
bias.
P. Yes. Okay, sir.
N is more, P2 is lesser potential, so it is a reverse
Yes.
bias.
Yes, sir. Get it.
Same thing. Okay.
Okay, sir.
Right.
Thank you,
Hello.
Please a bit faster because I don't have much time. We can discuss remaining questions tomorrow also, right? Okay.
Yes. So
Please,
in
last
conventional,
5 minutes I have. Yes. Yes.
in conventional thyristor with negative weight current.
Okay.
So in the same topic.
Yes.
Sir, if the potential we applied to that gate and cathode, if we increase such that reverse gate current becomes equals to the holding current, sir, in that case that SCR will turn off.
Please repeat the question.
Sir, if that reverse
Suppose
reverse
SCR is in a on state. First case is SCR is in a on state. Okay.
yes sir, so small IG we have applied reverse gate.
Okay.
Sir, in that the small portion of J3 is affected.
Okay. Correct.
Sir, if that gate current, reverse gate current is increased equals to that holding current.
Okay.
Sir, in that case, will that SCR will turn off?
No, SCR will not turn off at all.
Sir, why?
Because your holding current is having a relation with the anode current, na? What is the definition of holding current? It is a minimum anode current.
Yes, sir.
Whether it is related to your gate current, no.
No.
Right?
Sir, but that current, that reverse current will become to the anode current, no, sir. In that case, that depletion layer will form at J3, no?
Okay. You are saying that the reverse current becomes equal to anode current value means holding current value.
Yes, sir.
Yes or no?
Yes, sir. If we increase it too.
No, you can increase, even you can increase beyond that also. It will not affect on the conduction of the device because your holding current is in milliampere.
Okay.
Right? Your gate current is also in milliampere.
Yes, sir.
So what is happening if we are circulating the milliampere current now in this region? Okay. So only small portion was biased. But if we circulate, if we could circulate a high gate current na, then it may affect on the device conduction. But we are having limitation that whether our gate cathode circuit can withstand with a high current, no.
Okay.
Right?
Yes, sir.
So high current means I am saying that the current is in the range of 10 ampere, 15 ampere, 20 ampere, like this I am saying.
Okay.
Milliampere current, if you circulate, it will not affect on the device conduction, right?
Okay, sir.
Okay.
Hello, sir.
Yes, please.
Sir, in 23, yep.
23?
Yep.
Okay.
23. Sir, is IGBT bidirectional? Sir,
Is
not
IGBT? No,
bidirectional.
it is not a bidirectional.
Because if you have applied negative reverse voltage, it will conduct in reverse direction if you also VG the negative, sir.
Where I have applied the reverse voltage?
Across IGBT, sir.
Across IGBT,
If you applied reverse voltage and also reverse gates voltage, it will conduct in reverse direction, right, sir?
Okay, means you are saying for that N plus buffer thing, huh?
Yeah, without a symmetric IGBT.
Symmetric or symmetric?
Symmetric, sir.
Symmetric, you are saying. Okay. In symmetric case, just a minute. Means without N plus.
Yes, sir.
Without N plus, yes, you are saying that. Please repeat the question.
If you applied the reverse voltage across gate and emitter and collector, sir, along with reverse VG, reverse voltage, it will conduct in reverse direction, right, sir? Current.
Yes, it can.
Then we can say it's a 4-quadrant of like bipolar bidirectional.
Yes, you can say. But if buffer layer is absent.
Yes, a symmetric one. Symmetric IGBT.
Symmetric one. But most of the times the thing is by default, if we consider it as IGBT, na,
okay,
then it is like a asymmetric type only.
Okay.
Right? Okay.
So it's in page number 6.
Yes.
Page number 6, sir.
6.
Okay. So why we have to consider Q points?
Just a minute. Remaining students like Kalyan, Salman Khan, Shawan Kumar, Akshay, Tulsi. One request from my side. Shall we continue tomorrow? Anil? Right? Please today only please consider me because I have to go somewhere. Okay? Right? Please, you can continue.
Sir, why we have to consider these 2 points?
Some disturbance is there.
Okay, say Q points. Why we have to use?
Why we have to
use these Q points? That is load points. Load points, yeah.
These points.
Yes, sir.
Why means I am not getting.
Sir, why you are using these points like a load line?
Okay. Means I have drawn this. This is a load line.
Yes, sir.
How we have drawn? Just simple thing, whatever I explained here, right?
Okay, sir.
So the meaning is what? If I select VCC, any value, okay. Suppose
Okay.
this is like a VCC is equal to 250 volts. Suppose if I connect here 250 volt, and here I am having a load resistor RL is as some value, okay.
Okay.
Then what it indicates? If my base current is 0, na,
Okay,
then
sir.
it is like operating point is at this point, okay.
Cutoff. Okay.
Cutoff region. If I go on increasing the base current, my operating point will be shifting from cutoff towards the active region.
Okay, sir.
If I further increase the base current, it will be further increasing, means shifting in the upward direction, but
Okay.
on the load line only. If I further increase the base current, it will be like this. Similarly here, if I further increase the base current, it will be entering into the hard saturation region.
Okay.
Right?
Okay, sir.
Okay.
Thank you, sir.
Yes. Right. So please, we'll stop here. Okay. Remaining doubts will continue today. Sorry, tomorrow, not today, tomorrow. I think 2 more questions we have to discuss. Tomorrow we'll discuss those questions first. And after that, we will be discussing the new chapter. That is the rectifiers. Very important chapter as long as gate, ESC, PSUs are considered. And large number of contents are there in the rectifier. Okay. Compared to the other converters, rectifiers are having a wide content. Okay. We are going to discuss each and every bit in detail. Okay. Right. Thank you. Thanks to all of you.
Thank you.
Yeah.